Hello, can you hear me? Okay. Welcome, everyone. Welcome to the Lisbon Machine Learning School. It's a big pleasure to have here the president of Technico, who is going to say some words before we start. So please take a seat if you are not seated already. And Rogério Clássio, president of Technico, is going to start. Is Zoom working? It is. Okay.
Okay, no, that's it. Okay, good morning to you all. It's a pleasure for me to being here, giving you a warm welcome to this what is the number? The 14th Lisbon Machine Learning School. We now have the correct date. We are in the present here. So we are Instituto Superior Técnico is your host. We are the engineering school of the University of Lisbon. We are a school in which we have all the fields of engineering from ICT to mechanics, chemistry, and so on. So we are in the main campus of the university. We are this year celebrating our 113th anniversary. I hope that you enjoy of being here with us during this week, and I hope that you have some time to have the opportunity to see the campus of IST, to see the city of Lisbon, and have also a little bit of fun here with us during these days. So thank you very much and welcome. Thank you.
Okay, thank you, Rogério. So I'm just going to present some opening slides very quickly, and then we are going to have our first lecture. So this is the 14th edition of the school. The school is only possible thanks to our sponsors. So this is our list of sponsors. We have Google as our gold sponsor, Zendesk as our silver sponsor, and many supporters. One thing that I'd like to mention is that at Technico, at IST, we have a very strong machine learning group. We are part of the ELIS network. ELIS is the European Laboratory for Learning and Intelligent Systems. In case you are doing your masters and wondering what to do next, there's many opportunities for PhDs and master programs at IST that are related to these topics. So this year we have a large list of organizers that are essential to make this happen. I think they are almost all here. Most of them seated in the front row. There is also a steering committee that keeps track of how things are evolving every year and does the necessary adaptations for making the school being always up to date. And finally, most important, we have an amazing list of monitors that volunteered to help with the labs and with the other things in the school. So this is the complete list. I'm not going to say each name just for in the interest of time, but a big thank you to everyone. You can see them by wearing, because most of them are wearing the red/pink t-shirts, okay, the monitor t-shirts. So if you have any questions, find one of them and ask questions, okay. So these are some this is a map of the campus. The activities of the school are going to be somewhat spread in campus. The place where we are right now is this building, okay. This is also the building where we're going to have lunch in the ground floor. Today the welcome reception is going to be on this garden. Most of the afternoon coffee breaks are going to be here, okay, in another garden. And the labs in the afternoon are going to be in a different building, okay. So don't worry about these. You can just follow the crowd and you'll find all these places. But if you want to understand better where you are in the map, you can always look at this. So we also have some tools to facilitate communication and dissemination. We are using Discord this year as a platform for communicating about events in the school, Q&A, talking to students, posting slides and other information about the talks. There is also a YouTube channel where we are going to stream the lectures. and we are, the lectures are going to stay there recorded after the school is over. This is a recap of today's schedule. So we are a little bit delayed, but hopefully Mario will catch up in his lecture. So the first lecture is going to be an introductory lecture on linear models with two parts, with a coffee break in the middle. Mario, who I'm going to introduce in a bit, is going to give this lecture. Then there's lunch. For lunch, you should have some tickets when you registered, so you can use the tickets for lunch. I don't know if there is any specific recommendation that we want to give now about lunch. No? Okay. So you just, after the lecture is over, it's in the same building, so you just go up the stairs. Then we are going to have labs in the afternoon. And at 5, there's going to be a welcome reception with some drinks in the garden near the South Tower. If you don't know where is North and South, don't worry. We need to exit this building, turn right, get some stairs down, and turn right again. But if you follow the monitors, you'll get there. So other practical information. If you need internet, there is a EduRoam account that you can use. If you have EduRoam. If you don't have EduRoam, you can always join using the technical guest network. If you need, this is the username and this is the password. Okay, so I'll wait a few seconds if you want to take pictures of these. There is also more information in the website. You can see there the schedule, the speakers, and so on. We are going to post the slides of every lecture in the website as well. If you haven't done so, make sure to join the LXMLS 2024 Google group, where it works as a forum. Okay, so there was an email about that Fernando sent yesterday, I think. So you can just follow the instructions there to join. Okay, so on whoa, this is wrong. This should be Saturday. So sorry. So on Saturday, there's going to be a dinner, a summer school dinner at Casa do Alentejo. It's a little bit far from here. You can either walk, it should be like half an hour walk, or you can take the subway. The directions are in the website. If you want to get the map, you can just use these QR codes, okay, to get there. So don't worry, because these slides are going to be put in the website. You can always go there and check these again. And that's it. So enjoy LXMLS 2024. And now it's a big pleasure to introduce Mário. Okay, so oops. So Mário is a professor at Técnico and a researcher at the Instituto de Comunicações. He has lots of work in machine learning. I think I will spare the words. But he's going to, so he's also one of the organizers of the school since the first year. And his lecture today is going to be an introduction to linear models. So we are trying to make the cadence of these lectures, starting with the basics and then move on to more and more complex themes. And today is the introductory one. Okay, thank you, Mário.
Okay, thank you, Andre. So welcome everybody. So bear with me, because this is, I'm gonna change. So we've been giving this talk so far. I think I'm one of the two. Sorry. Oh, sorry. Yeah. Just a second. I need to go to Zoom. It's turned off. Yeah, I see what you mean. Sorry. This is what you mean, right? Yeah. Okay, thank you. Okay. So I think I'm one of the only two people who gave lectures in all the 14 editions, right? It's me and Noah Smith. Yes, but for the first 11 editions, I also had the first day lecture. It was a refresher and so remind you about basic stuff in mathematics that are needed in machine learning. So probability, statistics, algebra, optimization, stuff like that. But a few years ago, we decided that you've been coming to the summer school for so many years that you all know that stuff already. So we decided to change. And the first lecture now is about, and André started it, It's about linear models, and I'll explain why linear models in a second. And then actually last year I gave the linear models talk, lecture, because Andrea couldn't do it. And then this year I decided to change it completely. So it's again, it's a lecture on linear models, which I subtitled Foundations of Machine Learning, because that's my view of it. And so, but it's the first time I'm giving it. It's based on some part of my PhD level course on machine learning. So I'm assuming that you all are sort of at least master level students, PhD level students in machine learning, that you all know your basics in probability and statistics. I will assume that you know at least Bayes' theorem. So if you don't, let me know right now. Okay. So just to start to put things in perspective, so we're talking about classical machine learning, so which has some, if you Google, there's lots and lots of pictures like this about how to divide the different types of machine learning, and we'll be only on the left side, supervised machine learning, which is typically subdivided further into classification and regression, and we will come back to this in more detail in a second. We are on the left side. We will not be even touching or mentioning the right side, so unsupervised learning. So supervised learning, in a sense, and I always like to show nice pictures, is about learning from a teacher. So that a teacher teaching a child. So that's sort of what supervised learning is. So there's a typo in the title of this slide, so I'll hide it. So there's many, again, supervised learning, which is on the upper right side of that triangle. There's unsupervised, supervised, and there's also reinforcement learning. We won't touch any of that. So supervised learning, there are many things that can be seen as supervised learning that are supervised learning tasks, such as classification, diagnostics in medicine, prediction of, say, stock exchange rate, something like that. So those are just a few examples. So if you have a medical imaging, in that case, it's a skin lesion. Classifying into benign or malignant is a classification problem, of course. Or if you want, there's a very classical example up there, predicting the efficiency of a car from stuff like the weight and the horsepower of the car is a regression problem. So when you're guessing, you're trying to predict the quantity from other quantities. So why a lecture on linear models? Okay, so this slide is still Andre's slide. In 2024, deep neural networks are ubiquitous. So why waste time on deep networks, on linear networks, or on linear models? That's the best way to say it. Well, probably one reason is that old professors like to teach old stuff. So that's maybe the real reason. But there are many other actual reasons. So one of them is that the underlying machine learning concepts are the same. So if you don't understand linear models, you don't have the foundations to understand more complex models. It's like studying cells when you're studying biology. So the cell is the fundamental building block of life, such as linear models are the fundamental building block of almost all of machine learning on top of these. So it's much easier to understand and to solve in practice. Because it's much simpler. So they are still widely used, much more than it's publicized, because it's essential. In many situations, that's all you can do. They are, of course, a component of deep networks, as we will see. And it is, in my perspective, the natural and the correct starting point to start learning and studying machine learning. It's through linear models. So why is it a component? So if you have of deep networks, suppose you are training this big network to distinguish cats from dogs. Of course, the final layer of this network is a linear classifier. So we're going to look only to this box, essentially, not only for classification, but also for regression, and forget everything that's behind, which will be covered tomorrow in the deep learning lecture. So you're going to assume that somehow I have all the features I need from the image, from whatever, to solve my problem, and I'm going to focus only on in this final part, which will give us enough slides to go through. So just a brief introduction, so to slightly more formal to what we're going to look at. So since we are in a supervised learning context, that we have training data, which, as I'm sure you all know, is composed of a sequence of pairs. Each pair is an input and an output. So the input is which we'll typically call X, which will go from X1 to Xn, and the outputs are Y1 to and Yn. And I will not for now specify what X and Y are. They could be whatever, images, pieces of sound, whatever, and Y could be many different things too. So examples, and we'll follow in the next slide. So the goal, of course, is to learn a predictor. okay, some function that maps from the space, from the set where the inputs live to the space where the outputs live. Let's call it age. And now the goal is to use this age to predict the output corresponding to a new input. Okay, you have these, you want to guess the corresponding y, which is supposedly unknown. And so the many words are used to describe these. You can predict, or you can infer, you can guess, you can decide what you think, what the machine thinks, what age thinks that y is for that specific x. And hopefully, y hat, the prediction should be equal or close to the true y, which we don't know most of the time. And when this happens, we say that the machine, informally for now, we say that the machine generalizes. So it learned from these examples how to predict the output for new inputs. And if it does it in a good way, and there are many ways to formalize this, then we say the machine generalizes well. So examples of inputs and outputs. So this is for now pretty abstract. So input can be a piece of text, a news article, a sentence, an image, a signal, a collection of lab test results for medical examination, something, whatever. It doesn't really matter. And the output can be many things, so fake or true. If you want to build a classifier which will take a news article and try to decide if it's a fake or true article. A topic for a news article, what is it about? If for an image, it could be an image segmentation. Taking an image, I'll produce how the image should be segmented in meaningful pieces. If for a sentence, it could be the next words in the sentence, which is what large language models do. Is kind of they're simply taking as input some context and predicting what the next word is going to be. Could be a medical diagnostic. Could be the stock value of some thing you're trying to buy, thinking about buying tomorrow, investing. Could be the estimate of the maximum temperature in Lisbon tomorrow. Could be many different things. Okay. So input-output pairs, examples like I just mentioned, it could be a news article and a topic, a sentence and a translation. For example, machine translation is also a problem like this. You have an input and an output, and from examples, you want to learn how to generalize these examples to unseen cases. And typically, and we will follow these taxonomy today, supervised learning problems are usually divided into two types, depending on the nature of set y. Regression, when y is quantitative, it's a quantity. And it could be just a number, or it could be collection of numbers. So but the important thing is that they are numbers. They have quantitative meaning, and classification when the output set y is categorical. And the key thing here is that by categorical, I mean the set that does not have an order. So although we'll always refer to classes as 1, 2, 3, 4, 5, this is arbitrary. I could call them red, blue, green, gray, and there's no order. Okay, so the key difference between the sets for regression classification is that in the regression case, y is a set with an order or power set of a set with an order. In the categorical case, there is no order. It's just a bag of classes. So regression, in the regression case, the output can be the real line or the interval from 0 to 1 or just non-negative real numbers or whatever. Okay, so for example, you may be interested in given some article, predict how much time a user will spend reading it, which you will find if you there are many websites with articles that have a little number that says estimated time for reading this, and it's done by running some regression problem on the text. It's not, of course, it's a function of the length, but not only of the length. So in multivariate regression, that's another key word. Instead of predicting just a quantity, you predict a vector of quantities. So could be some number so a vector in RK or non-negative collection of non-negative quantities, or this mysterious symbol for some, maybe some of you know it, some of you don't, which is the simplex. It's just a collection of numbers that are non-negative and sum to 1, so they can be seen as probabilities. It's a simplex, and examples can be you're given a noisy image and you want to denoise the image. That's a multivariate regression problem. Or you want to do binary classification. In this case, the set is, say, something like -1 + 1 or 0, 1 or AB. It doesn't really matter because, as I said, now in the classification case, there's no order. So it really doesn't matter how I label the classes. It's completely arbitrary. So, but typically we say 0, 1 or -1 + 1, but you could say AB or something else, or red and blue or red and green or something. It doesn't matter. Multi-class classification, that's the usual name when we have more than two classes. So it's whatever is above binary classification, we typically call it multi-class. Not that binary is not multi, it's not mono, it's multi, but that's the usual name. The fundamental thing, and I stress this all the time, the key thing for classification is that the order is irrelevant. It doesn't really matter what this set has no order. Although for convenience, we typically write 1, 2, 3, 4, 5, not to write like red, blue, green, gray, because I will easily, quickly, and run out of names of colors or something else. The order is irrelevant, okay? So it's just a set, and sets have no order. So, for example, you can be interested in classifying documents in terms of topic about what the text is, or you can classify an image, or you can do word prediction in large language models. These are all multi-class classification problems. And finally, there is structured classification, where is a situation where the output set does not have a fixed size a priori. For example, if you're doing machine translation, the potential output depends on the input. Even the size is not predefined, okay? Because you can have sentences of different length, and so it can be exponentially large, and it's structured. It has a structure. It has, like in the text, it has order. Or in an image, it has image segmentation. It's a structured classification problem. You don't know a priori how many regions you will have. So features, okay? So we will assume, as I told you in the beginning, that we have features. So there's maybe a deep network or something else that extracted features for me. And for a long time, for many decades, actually, feature engineering was the core business of machine learning. How to extract properties of the object that I need to deal with that are relevant and useful to solve my task. Okay, so what features should I extract from a piece from text so that I can solve the problems such as classifying the topic of the text or something like that? So there's decades of research in these topics. So for text, the classical thing is bag of words and many other things. In imaging, there were hundreds and well, thousands and thousands of papers on how to extract features from images to solve, say, classification problems. SIFT features are a very famous example, which I will not at all describe. There are many other types of features. They can be categorical, they can be Boolean, say 1 or 0. There are continuous features, there are vector valid features, there are histograms, there are many different types of features. So it's a whole art. Okay, so feature representation, formally, we see them as a map. It's a function that maps from the space or set where the objects live, X, into some d-dimensional space. So a feature map is a function that takes an object, say an image, and produces a vector of numbers. Okay, or it takes a text and produces a vector of numbers. Okay, so you think of word embeddings. It's a feature extraction. It's a feature map. It may be very high dimensional. In practice, actually, in fact, it can even be infinite dimensional. In some cases, if we're using some sort of kernel methods. It can mix categorical and continuous features. Think about medical records for patients. They mix categorical and continuous features. It has I don't like the word continuous. I should have numeric features. Numeric features like weight, age, height, but it also has categorical features, gender, I don't know, nationality, something like that. So there's lots of problems where we have a mix of categorical and continuous features. And it's very common for categorical features to be represented by something called one-hot encoding, where instead of indicating a label for a feature from 1 to k, you have a binary vector, which is all zeros except in one location, and the location is precisely the class that is active for that feature, for that object, okay? We'll come back to this. So this is a notation that I'll come back to very often. E sub y just means a vector of all zeros of dimension, whatever the dimension is at the time, in this case k, with a 1 in position y and zeros everywhere else. It's called the one-hot encoding of y. Okay, so how do we find these features? So feature engineering is sort of alchemy. Okay, it's what people done for a long time. And in computer vision, for example, I'd say 90% of the papers published and all the research done until 2012 was about feature engineering, how to extract features from images to solve the problems that are relevant for me. It's usually very time consuming, and it requires deep knowledge of the domain. For example, to extract features for NLP, typically people would need to know a lot of linguistics and need to know about the structure of the language, what are the relevant features to solve a given problem. Of course, it has its good aspects. So the one of fundamental aspect, which is positive, is that it allows incorporating knowledge. If you know something about the domain, so you may be interested in actually designing the features because the features bring something that you know into the problem, which is sometimes called the inductive bias, or you're biasing the structure that you will obtain by bringing in knowledge about the domain that you have. Okay, it's still widely used in practice because especially in data scarce scenarios, it's much harder to learn the features than the final layer of the classifier. So if you don't have enough data, typically you cannot do feature learning, especially if you don't have any similar data. Of course, there's a modern alternative, which goes by the name of deep learning, but actually it also goes by the name of representation learning. It's not coincidence that one of the main conferences in deep learning, it's called ICLR, International Conference on Learning Representations. It's not International Conference on Deep Learning. It's called International Conference on Learning Representations because representation learning and deep learning are sort of the same thing. And tomorrow you have the lecture by Bikya Raj about deep learning. So this is probably the penultimate time that I will mention a deep network today. Okay, so let's go into the actual meat of the talk, of the lecture. So we'll start with regression. So this is an outline. It's a very simple structure. I have 3 sections: regression, classification, and then optimization for supervised learning. How to solve the problems that we will find in actual terms. And we'll start with regression. Okay, so let's start with a picture. Everybody knows what regression is. Everybody, even in high school, you've seen pictures like this. You have a bunch of points, you fit a line. That's linear regression in the simplest case. Okay, so if your grandmother asks you what is regression, this is what you say. You show her a picture like this. So there's a sentence that I heard a couple of years ago, which I like, which is, when you're fundraising, you say that what you're doing is AI. When you're hiring, you actually need people who know machine learning. And in the end, you end up just doing linear regression. Okay, it's not always true, but it's more often true than people actually admit it. And as we will see, linear regression can actually be nonlinear. Okay, because of the features, because we will assume that we have features. The features themselves may be nonlinear, and so I'll have a couple of these XKCD cartoons because I think I have a dream of giving a lecture only using XKCD cartoons, but I haven't done it yet. But it's this cartoon is very important, and I show it in all the talks I give about, even for lay people, about machine learning, that the way you do things brings a lot of baggage into what you're doing. So for example, you have those points, and you can fit many different types of curves to those points. If you fit a straight line, you can say, hey, I did a regression. But if you fit a polynomial, say a second order polynomial, you get this little bent curve. And so that's it. But now if you fit a logarithmic function, which you can also do, it seems that the trend of those points is like it's tapering off. Whereas if with the quadratic, it seems that it's actually accelerating. And it's not easy to tell which of these is better. You can also fit an exponential, and you say, oh, look, it's growing uncontrollably, or you can do many other things. So the way you choose the features and what you do with them brings a lot of influence into how you solve the problem. And so you need to be aware. So you need to be aware. You need to be aware of the fact that whatever we do in machine learning, we have an inductive bias: choice of model, choice of criteria, choice of optimization, choice of everything. You have lots and lots of choices, and these choices have impact in the final result. Okay, so what is regression? I'm sure most of you know. So I would say, who doesn't know what regression is? Never heard of regression? Great. So, okay, so this is, let me say something, let me open a parenthesis just for the philosophy of what I'm trying to do here. So I would not have the fantasy of thinking that someone who didn't see this before, who doesn't know what regression and classification are, that you will learn it in 3 hours. Okay, that's impossible. Okay, so if you know some of these, my goal is to tell a story that kind of brings together a set of these ideas in basic linear models, which start from classical regression and goes all the way up, as you will see at the end, to Adam optimization and implicit regularization and double descent, which are really modern topics. And my goal is mostly to kind of transmit the idea that these are nice things, they're interesting, so enjoy them, and feel, if you don't know them, but if you kind of had some idea, feel stimulated to go and learn more. And because these are really important foundations for machine learning. Okay, so regression, in a nutshell, as you all know, I will go fast, is the task of building a machine that knows how to predict or estimate or guess a quantity. So the key word is quantity, otherwise it would not be regression, from other quantities, quote unquote, because they may not be quantities, they may be categorical features. So from other things, okay? So say P of them. So you have an input which has P inputs, there's some mysterious machine that produces an estimate of Y. Of course, regression is a central tool in data analysis. So there are few scientific papers in any area that do not have a plot with points and a line, okay? So this is regression. So regression is a fundamental tool in most of science. Everything you have quantities and you're reporting experiments, results, observations. Almost always you have some sort of regression. So it's a fundamental tool in science and of course in engineering. And as we saw before, so we're gonna do this. We're gonna learn this machine or train the machine. I don't like the word train, but it's okay. From a collection of examples. You have a collection of examples, pairs, input, output, and the goal is to find the best possible machine. And to say what is the best possible machine, I need a criterion, okay? And just a note, so I will use bold to denote vectors and matrices from this point on, almost always. Maybe I'll fail a few times. So let me start a bit more technical now. This is the classical linear regression. So there are many ways to motivate linear regression. You could actually start with automatically, directly into say, let's do least squares. Why? Because it makes sense. But you can start more probabilistically, more formally, and say, okay, my model is that my observations, each observation, is obtained from some true underlying value, which is in fact some linear combination of x. So remember that. So this W transpose x is just a sum. It's just W1 times x1 plus W, it's D, right, times XD, or P, I think it's P. It's just a linear combination. So the x's are the features, the w's are the weights. You sum the weights times the features, you add everything, you add an extra term, so-called bias, and then to obtain the observation, you add noise. And just assume that the noise is zero mean and they have some variance sigma 2. And so from these, you immediately know that these responses, these y's, are Gaussian. Because the noise is Gaussian and the other part is deterministic, is fixed. You don't know it, but it's fixed. And so you can write down that the conditional density of the observations given the input, it's a Gaussian in the observations, which has mean W transpose X plus W0, which is the sort of the clean value that you do not observe, with some variance sigma 2. Of course, you don't know W and W0. That's the whole goal of the thing. But you have data. Okay. That's the difference. And so notice that I'm not assuming that these points x1 to xn are probabilistic. They are fixed. Someone gave it to you. I've observed these x, the response was this. For this x, the response was this. But the x, I don't know. I don't have models for x, only for how y depends on x. And so I can write the likelihood, and I'm assuming that you know what the likelihood is. So the likelihood is just the probability density function of all the observations of all the y's, given all the x's, and the parameters that you don't know. So W and W0, the vector W and parameter W0. And because I'm assuming that all the observations are independent, so Y1, Y2, Y3, they're all independent of each other, conditioned on X1, X2, X3, this ends up being just a product of all those Gaussians, okay? And so the usual thing that we always all do, so we resort to our beloved logarithmic function. We take the log of that. When you take logs, you transform products in sums. You get rid of everything that's constant is irrelevant. You get rid of everything. And so you find out that if you want to maximize the log likelihood, so you want to find the parameters that make the observations the most likely, which is what choice of W and W0 make these points the most likely, you find out that what you should do is minimize the sum of those squared errors. Notice that these, if I put them plus here and I look at these, and I put parentheses there. This is just something which I could call y hat. It's my prediction of what y is for point I, and I'm squaring the difference between that and the true y that was given, true or assumed true y that was given in the training set. Okay, so that's it. So the maximum likelihood looks like this. It's just a sum of squares of differences between the given y's and the predicted y's, which goes by many other names. It's also called least squares, okay, for obvious reasons. There's another way of seeing it, which is actually what you want to do is you find W and W0, so the vector of weights and the bias that minimizes the expected value of the difference between the prediction. Notice that again, this is the prediction with a plus here. This is y hat. I want to minimize the expected value between the prediction and the true y. Okay, and you could do this by definition. It's just how to compute an expected value. You have the joint density, you multiply by the function, you integrate. Of course, you cannot do it because you don't know the joint density. If you knew, the problem was solved. And so what you do is you replace the theoretical value of the expectation by the sample mean. So this is just a sample mean. You just average across all the points what was already above, which is the square of the difference between the predicted y and the given y. And this goes by the name of residual sum of squares or least squares. Least squares cost, or in more theoretical machine learning, is usually called empirical risk. Okay, the empirical risk, or REMP, is the empirical version of the actual risk, which is an expectation. So even if you didn't follow all of these from the probabilistic point of view, don't worry too much, because this will be our starting point actually. So we want to find W and W0 that, and I should have written this always like this, it's nicer actually, with a plus, because this is y hat y. I want to find W and W0 that achieve the minimization, the minimizer of this square of the squared residuals. It doesn't matter if I put the 1 over n or not the 1 over n, it doesn't change anything because I'm minimizing, so I don't care about the 1 over n. It's just a term. And also this goes by different names. It's empirical risk minimization, it's least squares, it's maximum likelihood, so you can derive it from different perspectives. So it's nice to know that you can arrive at the same criterion starting from different positions. So a picture that I like about these is, you can find it in the famous book by Hasty Shirani Friedman, Elements of Statistical Learning, which is now an example of regression in 2D, just to see what's going on. So if you call it linear regression, we're fitting a plane, okay, not a line. It's a plane, but it's a plane. It's not something that curves because it's linear, okay? And we're minimizing the squares of the residuals, which is the squares of these distances here, okay? So each of these red dots, it's a point given, which has x1, x2 coordinates down in the horizontal plane, and has a value y in the vertical axis. And these distances here, okay, are my residuals. So this is say yi, the point up there on the surface is yi hat, and this distance here is the difference between the two. And the square, I'm minimizing the square of these distances. So the final position of the plane is the position that minimizes the sum of the squares of these lengths of these black lines, which has a nice, it's not very relevant, but it's a very nice physical interpretation, which is if you had springs or bands attaching, if you imagine these red dots are fixed in space, and if this is a rigid plane and you attach those points to the plane using elastic bands, because I don't know if there are any physicists in the room, the energy in an ideal spring is proportional to the square of the elongation. You're essentially minimizing the energy that's stored in the system. So it's a minimum energy position that solves least squares regression. Not very relevant, but a fun thing to know. Okay, so one thing that I'll very quickly run over, because I know I have too many slides, way too many slides, and this is not the most interesting part. There are two ways to deal with this W0. It's a bit annoying to have this bias here. There are essentially two ways to deal with W0. So the first one is to assume that one of the features is 1, and so the first weight corresponds to W0. Okay, so it's simpler. We will not use this one, or we can, it doesn't really matter. There's another one, which is we assume that everything, all the data, so I'll go very fast here, that so the data is such that when you sum across all the points for each component, you get 0 average. And there's no loss in generality because you can always do this. You have a data set, it's a collection of points. You go at each component, you compute the average, subtract the average. So it's called centering the data, okay? So if you assume that the data is centered, also the same is true for the responses, then it turns out that the optimal W0 is 0, okay? And so you forget about the offset, okay? There's no loss of generality in this because in the end, you can always go put back the mean that you extracted. And so I'll get rid of I will not include W0 in the notation anymore from this point on, okay? So this is usually solved in vector notation, okay? So once we have this minimization problem of that I want to minimize with respect to W, now it's only W, there's no W0. So now this is what I'm calling Y I hat, okay? I can write these as in vector notation, which is that square of this Euclidean norm of the difference between a vector of y's. So I'll write it there. So the y bold y is a vector that has all the y's. X is the so-called design matrix. So design matrix is a matrix that contains all the x's one by one. So it has p columns, as many features as columns, as many rows as data points. And this is called the design matrix. This name comes from many decades ago from statistics, because in a sense, it's the choice of these points is the design of an experiment. You choose what to observe, where to observe, okay? By choosing the points in feature space that you want to have the response for. So I'm assuming again now that you know basic linear algebra and basic calculus, like how to find minima of things, like compute gradient set to 0. So if you compute the gradient of this thing up here, so you're computing the gradient of a square is very easy, just 2 times the gradient of what's inside, the derivative of what's inside. So in this case, you get 2 x transpose. This is transpose of x, so it's the matrix where you switch lines with columns, rows with columns, and you get this, the gradient is that, okay? It's easy to write down. And so once you equate to 0, you say, okay, my minimum is, I'll justify later on that this is a convex problem. You want to find the minimum or the minimizer, you set the gradient to 0, you solve for x. So that I'll use this notation, which I like, which is the solution with respect to w of some equation. Inside you have an equation. So I'm solving with respect to w an equation, which is x transpose, xw minus y equals 0. So you can easily expand. You can write this as x transpose xw equals x transpose y. And so if x transpose x is invertible, you can just invert x transpose x and solve the problem. This is a very classical result from statistics, which is called least squares regression. But be careful that this is only possible if, and this is it will become very important later on, if this is only possible, of course, if x transpose x is invertible, if you can compute this inversion, x transpose x, because if you cannot compute this inversion, you cannot compute this. And for this, you need, I'm assuming that you know what rank is. So you need, it's a rank matrix, a full rank matrix, X. Because the matrix is X transpose X, notice that X transpose, so X is N by P, X transpose is P by N. And so X transpose N is P by P, it's a square matrix. Any matrix of the form matrix transpose itself is square. And so it's a P by P. And so to invert the P by P matrix, you need P non-zero singular value. So it needs rank P, which is only possible if N is larger or equal than P. So this is not possible if you have fewer data points than the number of coefficients, okay? So this is the classical regime, which is called large N small p. You have a few parameters that you want to estimate, and you have a lot of data, okay? N larger than or equal than P. Typically, hopefully, N much, much larger than P, which means you have a lot of data, okay? So once you do these, there's one you'll find in all papers that have regression. You'll find reporting this number called the coefficient of determination, R squared. And recall that we are assuming that the average of the responses is 0, so W0 is 0. So the average, the coefficient of determination is easy to explain visually. Okay, I'll probably just show it visually. It's like this. Suppose you fit just a horizontal line to the data, and you compute the sum of the squared residuals, which is the sum of those areas of those pink squares. And then you do the fitting with the model that you have, and you do again, you compute the sum of the residuals, which is the sum of the areas of those blue squares. And R2 is 1 minus the ratio between the two, okay? And this is called, sometimes it's called So 1 minus FVU. FVU stands for fraction of variance unexplained. Okay, so the higher the better. Okay, because you want SSR to be small with respect to ESS. So you want the sum of squared residuals to be as small as possible. So if you have a perfect fit, SSR will be 0. And so you have R squared equals 1, which is perfect fit. So the line going exactly through all the points. Okay, so there's another XKCD cartoon for you. We did this, they did this straight line fit. They found out that R2 was 0.06. And the comment is, I don't trust linear regression when it's harder to guess the direction of correlation from the scatter plot than to find new constellations on it. So if you see stuff with small R squared, of course, it's not the fit is not very good, although there are many other issues. But this is the basic one that everybody needs to know about linear regression. Another very important topic, aspect, which is fundamental for modern, actually, even for deep learning, is something called a hat matrix, which is once you do the regression, you can go back and look at what is the values on the line or on the plane exactly at the same position where you had the points in the training set. Okay, suppose if you have a line, it's easy to explain what this is. So you have some points, you fit a straight line, and now you want to know what is the value. So for example, this was an observed point. What is the value on the line? What would be the clean version of this observed point? Okay. So it's a predicted values at the sampled points. And now, because you already know W, you estimated W, you just multiply by X and you get those points, okay? And so because you know how to write W hat, it's just X transpose X minus 1, blah, blah, blah. You multiply everything together and you call these the hat matrix, okay? P. So P is called the hat matrix because it's the matrix that puts the hat on Y. You start with a Y without a hat, you end up with a Y with a hat. Okay, so who hadn't ever heard about the P matrix, the hat matrix? Everybody heard about the P matrix? Wow, great, excellent. Or are you just shy? Okay, the P matrix, great, so you know it. So the P matrix is a projection matrix. It is idempotent, although idempotent does not imply it's a projection, but it's idempotent is a matrix that when you multiply by itself, you get the same matrix again. Like a projection, right? If you project, and then you project again, the point does not move anymore. It's already projected, right? So it's a projection matrix, a projection where, okay, I'll skip the details. It's a projection there. So Py, so the hat, the values, are solving these. So what are the points in the range space of X? Notice that Y hat, Y hat is of the form X times something. So every time you multiply a matrix by a vector, the result is a linear combination of the columns of the matrix. Okay, it's called the range of the matrix, and so the y hat is in the range of X. So so that's formally a projection. You're looking for the point in the range of X, Z, that's as close as possible to Y. Okay, so in pictures, this is what it looks like. Okay, when you're doing linear regression, you're essentially solving a projection problem. In Rn, not in Rp, Rn is the number of data points, n is the number of data points, where y here is the vector of, the red vector is the vector that has all the responses, y1 to yn, okay? On the horizontal plane here, you have the range space of the axis, okay? So it's the columns of matrix X. In this case, I'm only using 2, otherwise I cannot do a picture. Not me, the picture is not mine, actually, I should have referenced. And when you're computing y hat, you're simply projecting the y vector down into the plane that is representable by linear combinations of columns of X. Okay, that's what's happening when you do linear regression. Okay, how do you go nonlinear? So say, okay, this is too trivial because no problems are linear. Like dividing problems into linear and non-linear is like dividing all animals into elephants and non-elephants. Almost all animals are not elephants. There are many other types of animals. So why would we care about elephants? Well, they're nice, but why would we care about linear problems? Because even nonlinear problems can be written as linear problems, as probably many of you know. Okay, and so the trick here is just to express the new version of X as going through this nonlinearity phi, which will allow me to have a nonlinear function of X. Okay, the key thing is that I will not learn these functions. So this is when things become complicated. I will assume that these functions are fixed. So phi 0 to phi d minus 1, so I have d of them. Typically, I fix phi 0 to be a constant, which will take care of the product by W0. Okay, it will be the offset. But this feature multiplied by W0 will give me the offset of the function. And so it's just a mapping that goes from RP to RD. That's it. And these components are often called features. So the components of phi are the features, and phi is a feature map. For example, this is my second picture of a deep network. We can be looking at the final layer of a deep network. I'm ignoring everything that's behind. It has an input x1 to xp, so the input of the network, lots of complicated stuff. And then in the end, when you arrive at the final layer, you have, say, dimension d numbers, which you then combine linearly, add some bias, and sum. Okay, and in regression, that's all you need to do. Okay, it's just you get a number at the output. Okay, so you can actually not change anything we've done up to now if you just redefine what the X matrix means now. Okay, now the design matrix, instead of containing the points, it contains the phis of the points. Okay, it's no longer an n by p matrix. Now it's an n by d matrix because we have d features. Everything else is just the same. Okay, so you don't need to worry. So actually, it's common to say, okay, X, I'll just deal with X or phi of X. It doesn't matter because someone gave me those features and I don't worry about them because I'm not trying to learn them today. Okay, I will assume that they're fixed. Examples, which I'll very quickly run over because I don't want to waste time here, could be if you're doing polynomial regression, one way of doing it is to do regression using these features, which is all the monomials of order up to k if you're doing order k polynomial. If you're doing polynomial regression in multiple dimensions, or in 2 or d, the feature map is all the monomials of up to a given order. Okay, so it's that's how the features transformation do it. It's just a dimension, how many of them. There are many other things like radial basis function in classical machine learning. There was a lot of work around this. Gaussian RBFs, in-place splines, all sorts of things. Kernels, which I'll mention briefly. And so just to picture the idea, if you want to do regression using, in this case, radial basis functions, essentially the points are those dots. The fitted function is that red line that follows the dots. And that red line that follows the dots is just a linear combination of those other Gaussians. Okay, those functions are fixed. You just estimated what constant was multiplied by each one of them before I added. And that's a linear problem. It's just linear regression. It doesn't look linear, but it's just linear regression. So linear with respect to the parameters. That's the fundamental aspect, not with respect to the input. This is not a linear function, of course. But the problem that we solve to find this function is linear with respect to the parameters. Okay, so what happens if the rank of X is less than P? You don't have enough data, for example, and number of data points is less than the number of coefficients in the regression. Okay, the size of the feature vector. So you cannot compute least squares because the problem is that you cannot invert X transpose X. It has it's called a rank deficient matrix. That's what's written in there. So the classical thing to do, which I'm sure many of you know, is ridge regression. You just add something to the loss. So without this part here, this is just least squares regression. You just minimize the sum of the squares of the residuals. With this part here, you're also penalizing the norm of W. Okay, you're trying to say that W should not have too large a norm. You want to minimize the residuals, and you want to also minimize the norm of W. And there's a parameter lambda that controls how strongly you are imposing both goals. And it's easy to do. I'm not going to do it in detail. Just compute gradient set to 0, and the solution is that. Okay. Notice that with respect to least square solution, we have this new term here, plus lambda identity. Okay, in the inversion. And because now I'm going to appeal to your strong knowledge of linear algebra, because X transpose X is a symmetric and positive definite matrix, positive semi-definite. In this case, it may have 0 eigenvalues. And I'm sure you remember that the eigenvalues of, when I add identity to a matrix, the eigenvalues all shift up by one unit. If I add lambda times identity, the eigenvalues all shift up by lambda. So because this is a positive semi-definite, there are some 0 eigenvalues, some other eigenvalues. Everything shifts up by lambda. So if lambda is strictly positive, this matrix is always invertible. So by changing the matrix into X transpose X plus lambda identity, you get a matrix that's always invertible as long as lambda is strictly positive. This can be seen as a map or an MMSE. So for those of you who know, minimum mean squared error estimate of W under a Gaussian prior, but I will skip this. So this idea of adding this thing here, okay, goes by many names. It was reinvented and rediscovered many times along the history of these things. In neural networks, for example, it goes by the name of weight decay. It goes by the name of penalized least squares. It goes by the name of Tikhonov regularization. It goes by the name of L2 regularization. It also, in some cases, goes by the name of Wiener filter. So it has many different names depending on the special structure of these matrices. So just an illustration. This is from Kevin Murphy's book. Even in the case where you have n larger than p, it may be better to use ridge regression, so to so-called regularize the estimate, because it may lead to lower MSE. So this is an example in Kevin Murphy's book, fitting an order 14 polynomial to 21 points. So you have 21 points, so n is 21, p is 14, so you're okay, you have more points than dimensions. So you could solve least squares. And this is almost what you're doing in the upper left plot. You're solving least squares. So it's not you're solving ridge regression, but with a very small lambda. I don't know if you can read, log of lambda, so that's natural log ln of lambda is minus 20. So it's a really, really small lambda. It's almost like least squares. It's not least squares, otherwise you would almost, it would be more bumpy, but it's almost least squares. And the bottom plot is when for log of lambda equals around minus 8.5. And so on the right side, what you have is as a function of lambda, horizontal log lambda. You have in blue the training MSE, so the mean squared error, so the final residual. And you see that the smaller lambda, the smaller the residual, okay? Because you can actually minimize it. It's minimizable. The matrix is invertible. But what you see in the red line is the test MSE. Now you take more data points from there, some underlying true function, which I don't know what it is. And then you can test your predictor on data that was sampled not from those training points, but for other data from the same function. And you find out that the optimal value to use it somewhere over here, this is the one that achieves the smallest value. And so even in cases where you can compute least squares regression, often you don't want to do it because it's always good to put a little bit of regularization, although we'll see otherwise later on. Another very important quantity in regression is called degrees of freedom, which is the trace of the hat matrix, which is called degrees of freedom for the following reason. I'll show you a picture and you will understand why. So this is in a linear regression problem with a very simple data set. It has, I think, 200 or 300 points, 8 coefficients. 8 coefficients, so it's a small, low-dimensional problem. And when lambda is 0, which is the right end of the plot, those are the least squares estimates of the coefficients. So those are the names of the variables. It doesn't really matter what it is. It just says those are the least squares, and all 8 of them are non-zero, okay? Which means, or all 8 of them are whatever they are. So in this case, when lambda is 0, you have 8 degrees of freedom, okay? And as lambda goes to infinity, with you regularizing more and more and more, all the points go down to 0, okay? And so in that case, you have degrees of freedom 0, okay? So the idea is that by increasing lambda, you're constraining the freedom of W to be what it wants to be. So, okay, you start with completely free W when lambda is 0, and you end up with a completely non-free W, which has to be 0, and in the middle you have this. And the way to measure how free the estimate is by computing the trace of the P matrix, which is called degrees of freedom. There's a lot of work on how to compute degrees of freedom for more complicated estimators, but I will not go over this. So how do you choose lambda in practice? Okay, so how would you know how to choose lambda? Of course, if you, it seems like it's always better to choose smaller lambda because the training error is always as small as possible if you choose a small lambda. But so the way to do it is to not use the training data, of course. And the classical way is cross-validation, which I'm sure most of you have seen. So but in one slide, it's just you have available data. You create disjoint K, disjoint subsets. If you have K of them, n points, you have n over K samples in each of those subsets, S1 to Sk, okay? For each K in 1 to K, so if you have K subsets, you learn the parameter, let's call it WK hat ridge with coefficient lambda from all the samples not in Sk. So you take all, if you have K equals 10, you leave subset number 1 out and you train from all the subsets 2 to 10, okay? And then you compute the minimum squared error of the resulting using only the subset that you left out. Okay, only that one. And then you repeat these over all the subsets. So you leave the first one out, you train on the others, test on the first one, leave the second one out, learn on the others, test on the second one. You do that for all of them. And then in the end, you average everything and you choose lambda that minimizes the average of these prediction errors. This goes by the name of cross-validation. Common choices for K are 5 or 10, or if K is n, little n, so where you leave only one point out and train on everything else and check what happens with this point and then repeat for all possible points. This is called leave one out cross-validation, or LOOCV, LOOCV. Okay, you leave just one out, but it's very expensive, of course. No one does, unless you have a very small problem, which is very critical and very hard, and it's very important to tune lambda. It's very expensive to do leave one out cross-validation. Although in the linear regression case, there is a way to write the leave one out cross-validation error in closed form without having to actually solve it, but I will not go there. Okay, now let's look at something more interesting, which maybe you haven't seen. I will assume that everything I've seen up to now is part of what would be a standard basic machine learning, statistical machine learning course, like first 2 lectures, going slowly, of course, much more slower than this. This is now a bit going towards more modern things. Okay, so remember that when we're solving ridge regression, the problem looks like this. Okay, this is what we're solving. And we end up like writing xtx plus lambda I minus 1 xty, remember? So that's the w hat equals this. Okay, that's why it looks like this. So let's do something which looks stupid, which is let's rewrite this equation as it's on the right side. I'm going to take this identity times w, move it to the other side, okay? And then divide everything by lambda, which seems stupid because now I have the coefficient that I don't know, the coefficient vector w, appearing on both sides of the equation, which is something you really don't want. When you want to solve an equation, you usually want to put the unknown in one side alone, equals to whatever is on the other side. Now I'm on purpose splitting it and making it appear in both sides, okay? And the reason for that is to show that w, because w is written like this, as it's here, okay? It's clear that w is of the form x transpose, as you just look up there, x transpose times something, okay? And that something is what this, I'm calling it alpha. It's 1 over lambda, y minus that. And this is a very clear thing. This is the residual, right? Because this here is, this little part here is y hat, okay? It's x times w hat is y hat, okay? So that's alpha. So this shows that w, okay, w hat in ridge regression is a linear combination of rows of x, not columns, because it's x transpose times alpha, but rows, because the columns of x transpose are the rows of x, okay? What are the rows of x? The rows of x are my data points, x1, x2, x0, which means that w hat in ridge or least squares regression is a linear combination of rows of x. Just as y hat was a linear combination of columns of x, w hat is a linear combination of rows of x. And this will play a fundamental role in many things in modern deep learning, as we will see. Or in modern learning, I'd not call it deep, okay? Now, if you want to predict the value at some new point, of course, we know that predicting a value at some new point is just taking that new point x and computing the inner product with w hat, okay? But w hat looks like this, so it's because it has this form, right? Oops, why don't this? It has this form. It can be written simply as it's a sum of alphas times the inner product of x with the xi's, okay? Because this is just an inner product, and the other one is also just a collection, so it's a sum when you multiply a vector by a matrix. It's just computing the inner product with all the rows of the matrix. And so that's it, okay? So the response, you can write the response in linear regression, and once you compute the weights, in another way, which is different from what's usually written, which is, it's a linear combination of the inner product of my test point with all the points in the training set. I typically don't want to do this, because storing all the points in the data set to compute these is much, much more expensive than just storing W, okay? You would typically want to store W, but this is just an important observation that will open the door to a few things, okay? So this is the question we had in the previous slide. So rewrite the ridge in this way. Now, of course, we need to know alpha. If we don't know alpha, we cannot write these. Let's solve for alpha. So it's easy. We can insert this first equation x. So W reach equals x the alpha on the right side. Solve for alpha, and we get that. Okay. Notice that it's an interesting equation because it looks almost like classical ridge regression. The other one was x transpose x plus lambda I inverse. This is x transpose. It's in the reverse order. Okay. And so it means that W reach can be found in two different ways. You can either do the classical thing, which is the one on the right, x transpose x plus lambda I, blah, 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 which is a p by p inversion. Or you can write it as in the left side, because that's alpha, which is an n by n inversion. Okay, so you can choose between inverting an n by n matrix or a p by p matrix. Your choice. Which one you will choose, of course, if p is less than n, you will choose the second one on the right. That's the classical regime, where you have many more points than coefficients. On the left side, you have let's say, the interpolating or modern regime, where you have more coefficients than data points. So in models where you have more parameters than data points, this matrix on the left side is much easier to invert. Okay, you can write in whichever way you want. You can use it. And notice that this matrix x transpose, element ij of this matrix, is the inner product between the sample I and the sample x, xi inner product with xx, which goes by the name of Gram matrix. If you've seen, who has seen support vector machines in some course? Many people. So you've seen these from a different perspective, derived using convex optimization for the hinge loss or for the criteria for support vector machines. But you can also do it exactly in linear regression. It's much simpler, and you can get exactly the same. You end up with a Gram matrix. You end up with the so-called dual variables. So these alphas are the dual variables that also appear in support vector machines. So I'm not going to go into support vector machines, but only into linear models like this. Okay. So if you want to go nonlinear in this format, in this approach, as we saw before, the only thing you need to do is to introduce a feature map. Feature map is something that maps from the original objects x to phi of x. And so because you can write the prediction as a linear combination of inner products, now you have inner products between feature maps. It also appears in support vector machines. And the alpha is solved by inverting this matrix. Okay, this is not a support vector machine. I'm doing least squares. That's why we have a closed form solution. In support vector machines, we don't have a closed form solution. We need to solve a quadratic problem. But I'm doing linear regression, not a support vector machine. But it's the essentially same idea. Still the Gram matrix, that's what I need to deal with. It's this Gram matrix that has all the inner products between all the mappings of all the points, all the pairs of points. So now it seems like the feature map moves the inner product from RP to RD. Okay, and if RD is bigger than, is D is bigger than P, this could be really bad. Okay, is it bad? Let's see. Actually, let's not see, because I want to skip this. This is just showing that this is just the kernel trick. I see a lot of people have seen SVMs, just to show that the kernel trick also appears in linear regression. And in the end, you always have to do everything is only in the lower dimensional case. You have Mercer's theorem, which you've seen. I'm going to skip this. Okay, I'm going to skip the kernels. Kernels are very nice because they encapsulate the optimization problem from the data. As long as you have a kernel that extracts features from the sub-object, or more importantly, a kernel that specifies how similar two objects are, you can build everything on top of that, and you don't have to worry about the details of the data. So, but I'm going to skip this because otherwise, I'm going to skip the kernels for now. There are kernels for all sorts of objects. So for about a decade, from the mid-90s to the mid-2000s and the first decade of the 2000s, a lot of machine learning was devoted to kernelizing all possible methods that existed by inserting kernels in the formulation. So I'm going to skip kernels on strings, kernels on this and that. Okay, now this is more interesting, okay? Or much more, say, recent or more actual, more relevant for what we are looking at today. So consider that, let's go back to the problem, to the case where we have fewer data points than number of parameters, so n less than p. Still linear regression. This is, of course, this is all more complicated. If you look at deep learning, this is all much more complicated. The beauty of linear models is that you can do everything using simple math. So we have least squares regression. We know it does not have a unique solution. We know we cannot solve it because X transpose X is not invertible. And that's why I wrote there, W hat least squares belongs to the set of minimizers. So I want to minimize this residual. And notice that matrix X in this case is why doesn't this change? Yeah, is like this. It's wider than taller. It has N is the number of rows, P is the number of columns, and Y is something like this. Is this size? So there's many ways of combining columns of this matrix to become equal to Y. Okay, because you are in n-dimensional space, you have more than n vectors. So there are many linear combinations with vectors that you can find, actually infinitely many, that will give exactly Y. So it's easy to solve this. This is a 0. Okay, the argmin is whatever W is, but the argmin is the minimum is 0. Okay, okay. There are infinitely many solutions to this problem. So because X W equals Y, there's infinitely many solutions. There's uncountably many, so it's actually a subspace. That solves Y minus X W is 0. Okay, precisely because you're in an n-dimensional space and you have more than n vectors, the columns of W. Okay, so what do you do in these cases? Typically, you choose among all the vectors that achieve 0 residual, you choose the one that has the minimum norm. Okay, this is called the minimum norm solution. And the solution, it's written there. You minimize the norm of W under the constraint that W needs to be such that XW equals Y. So you have 0 residual. Among all the vectors W that give 0 residual, you choose the one that has the smallest norm. And this can be solved easily. I'm not going to derive it, but it's a classical thing with Lagrange multiplier for the equality constraint, and then you solve it, and then it's very easy. And you get that. It's similar. It looks a bit similar. Remember that the least square solution looked like this, right? It was X transpose X minus 1, X transpose Y. This is X. It's kind of the other way around. It's X transpose X, X transpose minus 1, Y. Okay, now notice that X transpose is N by N, not P by P. Okay, so it's smaller in this case because N is less than P. And so this can be inverted. So these two, so the least squares and the minimum norm solution are two instances of something called Moore-Penrose pseudo-inverse. So I don't know how many of you have heard about this. So the Moore-Penrose pseudo-inverse is sort of generalizes the notion of inversion of a matrix for a linear system. If you have a linear system that's overdetermined, more equations than unknowns, then you need to find the least square solution, which is the one that we've been doing up to now. If you have fewer equations than unknowns, which is this case, it's an underdetermined system, you find the minimum norm solution. There are many solutions, you need to choose one. So in this case, in the other case, there is no solution, so find the least bad one. In this case, there are many solutions, choose the best one, choose one. Okay, how? Maybe minimum norm, why not? It's a criterion as good as any other. Okay, so we are in the so-called perfect interpolating regime. Okay, because we are under this constraint here, we know that this thing solves precisely Y hat equals Y. So there's no error, there's no residuals. Okay, it's called perfect interpolation. You get 0 training error or learning error, whatever you want to call it. Okay, and this is at the heart of some modern observations. This started in 2019 with a paper by Misha Belkin, and a few other people, which is called the double descent. It's a phenomenon called double descent, which can be analyzed using this thing that we just saw in the simple train. So on the left side, you have, who has seen the double descent thing before? Quite a few people, great. So on the left side, we have the classical regime, where you have this complexity curve trade-off between complexity and generalization error. We have training error going down as the capacity, say the complexity. In this case, it will be the size, number of number P, number of parameters going up. There are many ways of formalizing this. And we know this is a classical regime that you find in all the books on machine learning up to 10 years ago, or even 8 years ago. Where there is this, in the test risk, there is this sweet spot, which is the actual complexity where you don't overfit. So it's considered that if you go too far into the right, you're overfitting, and then the test goes up again. But it was found out that people started noticing that this is not explained why deep networks work so well, given that they often operate in this mode where there are more parameters than data. You can actually find zero training error and still degeneralize well. And so a lot of research has been done around this, and it was found this is the classic, this is hand-drawn, it's not an experimental curve, but I'll show experimental ones in a second. Where if you keep on going beyond the interpolating thresholds, so where you can reach zero training error and you keep on increasing the complexity of the model, then the test error goes down again. Okay, it's called the modern. Modern is a very dangerous word because in 10 years it will sound strange, but now it's still pretty modern. Interpolating regime where the test error goes down again. Okay, this is why this is called a double descent, because there's a first descent, then it goes up, and then it descends again. Okay, these are a couple of pictures from Misha's paper. So these are now actual experimental data. So this is with something called random Fourier features. So each of the feature value, each of the feature maps f phi. So these features that map x into phi of x have these components, and the components are very simple. It's just exponential of square root of -1. That's j for the engineers, I for the mathematicians. Inner product between x and some random vectors. Okay, it's just random vectors. Okay, that's how you compute the features. You have a collection of random vectors. You have your new point x. You compute all these inner products, take exponentials multiplied by minus. So this is, it's called Fourier features because this looks like a Fourier basis, exponential of square root of -1. And the VIs are just the Gaussian thing. So it's just, think of it as sort of a polynomial regression with the order growing up, but it's not polynomials. It's some complex sum functions, okay? The important thing here is that polynomials are not good for these because as you add more and more order, the functions start getting more and more complicated, okay? And here, the functions all have the same sort of complexity. It's just a bunch of points, okay? There's no distinction. All this function, you can add more functions and they have the same nature as the functions that you had before. So that's the plot. On the left side, it's for 0-1 loss, which is not, we haven't seen it yet, but on the right side is precisely for linear regression. Okay, and then you have the double descent curve. So that's the test error. It goes down and it goes up and then it goes down again. Okay, and this is based, I don't know how many points. It's I think 20 points or something like this. It's a small problem. On the bottom, the orange line here on the bottom is the training error. As you see, as beyond a certain number of basis functions, you reach zero training error. And the blue curve is the one that's most interesting, which is the norm of the estimate. It's the norm of W, okay? It starts by being small, then it grows up, and at the threshold, it's really hard. It's really high. The thing is, at the threshold, you're not solving. Notice that the problem that you solve changes at the interpolation threshold. You change from solving least squares, which is x transpose x minus 1 xt, finding the coefficient vector that achieves the smallest possible error. And so you're not controlling for the norm of W, and W chooses its own norm to be whatever it needs to be. And beyond the interpolation threshold, you cannot solve that problem again. So you switch to solving another problem, which is from all possible W's that achieve zero error, let's try to make it small norm. Okay, and so you see that the more dimensions it has, the more chances it have to fit the data with the smallest norm, with the smaller norm. And so that's why the norm now keeps going down, okay? It goes down and down and down, and it goes to some asymptotic value, okay? So this is experimental data on a small training or a small toy set, data set. And now if you interested, if you already know about this, great. It's a very interesting topic. I think there's lots of papers. There's a very interesting paper last year called a U-turn on double descent, which analyzes this from a very different perspective, which is very interesting. This is another example. Again, this is the same picture. It's with different types of features. These are called ReLU features, where you have a bunch of vectors, VI again random, inner product with X, and then max between that and 0. And you have exactly the same. This is a beautiful plot with the exact behavior. This is for experimental data. It's in that paper that you can find easily, with a clear, very, very clear double descent and a huge spike in the middle at the interpolation threshold. Let me try to yet another example because it shows. So this is now another type of feature. It doesn't really matter. Legendre polynomials, it could be something else. And you see again that in the overparameterized regime on the right, the minimum value is smaller than the minimum value on the left. And let me just show you, this is the interesting picture for now. So the true function is that blue line, like it's a sine plus some slope. And the black dots are the data points, okay? On the left, you have in the underparameterized regime, so you have fewer basis functions than data points. So you underfit the data points, okay? It's not very good. At the interpolation threshold, you have polynomials of the order of the number of points. So everything goes completely crazy. It's those points down here. So you have, it's almost interpolating. So it's exactly interpolating in the middle, but outside of the points, the function just goes crazy. But as you keep on going, it's the upper right picture. The function now starts to, because it has enough coefficients to give it room to minimize the norm of the coefficients. And so the function starts behaving better and better. And if you go way to the right, you get something that is way over parameterized, but it's fitting, it's interpolating the points. Notice that the function is strange, but it goes exactly through the points. It has 0 training error. And between the points, it's not crazy as it is in the around the interpolating regime. Okay. So the tool to understand this is the fact that in linear regression, when you're in the n small np regime, you're doing minimum norm solution. So you're actually implicitly regularizing the solution by choosing the minimum norm of the coefficients. Okay. We should go for about 1 hour, 20 minutes more, then we stop, and then we have a break, and then we come back. Okay, so there I have a couple of slides on the Bayesian view of ridge regression, which I have 2 more things about linear regression, which is the Bayesian view, and then Gaussian processes. I will skip Gaussian processes, okay? But you'll have the slide. So what is the Bayesian view of ridge regression? It looks a bit weird. So we know, we already saw this because that's where we started, up there. Okay, we started by writing that I have a probability density for the responses, for the y's, for the observed y's, given W. And so for some reason, a stupid reason, I should have the design, no, not stupid reason, there's a good reason, I'll show you in a moment why. What I've been calling up to now the design matrix X, now I'm calling D, okay? Because I'll need X for something else. But it's a design matrix, so here you will recognize it on the right. It's just Gaussian observations. The true underlying values would be D times W, or it was X times W before, with some noise sigma 2. And now suppose we have a Gaussian prior for the coefficients. So 0 mean, some variance lambda, or 2 lambda, whatever. It's lambda, okay? Now, because everything is Gaussian, I'm not going to do it here in the lectures, I will do it on the board. It's very easy to write the posterior. You just multiply a Gaussian likelihood by a Gaussian prior, everything is closed form. Beauty of Gaussians is you can do everything is closed form. Gaussians turn everything into linear algebra. So it's just linear algebra. So you can write down that given those observations y, you know that the posterior for W, so W, which is the unknown parameters, follows a Gaussian distribution of which you can compute the mean. Notice that the mean is just ridge regression. This is just W hat ridge, okay, with coefficient sigma 2 lambda. Okay, that's it, nothing more. And then there's a covariance. Doesn't matter. It's again a matrix that also appears in ridge regression, but it's just you can compute it in closed form. That's the key thing. Okay. So what is useful? Well, if you want to predict the response at a new point, now you know what to do, how to do it, because you know that a new point, the prediction at a new point will be W times the vector at the new point X plus some noise, and you know the noise has variance sigma 2. So you know exactly what the density of the new point will be. You know everything. You know it's Gaussian because inner product of a Gaussian by a vector will give you a Gaussian again. Adding another Gaussian will give you a Gaussian again. Everything stays Gaussian, and you can write that the density for the predicted value follows a Gaussian. Forget about all the details, doesn't matter. It's just a Gaussian, okay? Which you know how to compute the mean and the variance. And the important thing to notice is that the variance, which is all of these here, depends on where you are, okay? So you know that if I want to predict here, my uncertainty would be this, but somewhere else it's different. So the uncertainty will change I will show you a picture, of course. So the observation is that the variance or uncertainty of the prediction depends on where you're doing the prediction, on X star. Actually, that Gaussian actually it can be written as it results from integrating that. It is your essentially you would like to compute if you're just using these. This is the density of the prediction y at a given point x with a given w value choice of w. If you would just plugging in, if you had some w hat and you plug it in there, you get the classical prediction, which is the value on the line. But now you have more because you integrate with respect to the uncertainty. You have uncertainty in w, so you need to say, if w follows this density, what density will the response follow? And that you get it by just multiplying and integrating with w. And let me show you this picture first. So this is what you get out of this, okay? So suppose it's very, very simple. Again, a picture from Kevin Murphy's book. So you have these 5 points. You fit a second order polynomial, linear regression. If you just do what we've done, least square solution, take w hat, plug in the polynomial, you know the variance of the noise, suppose you know, and so that would be what you get if you don't use the Bayesian view. Well, in the Bayesian view, which is using the expression in the previous slide, you have a closed form expression for the variance at each point. So that if you think of a grid, horizontal grid for possible values of x star, where you want the predictions, the height of those error bars are just the variance or the standard deviations, square root of the variances, or two times that, I don't know, which shows that, for example, around when you're not too far from the points, the uncertainty is not too high, but as you move away from the points, the uncertainty increases because you don't have observations there. Okay, so you have a closed form expression for the uncertainty of the prediction if you do the Bayesian view of linear regression, which you can think of from another perspective as sampling from the density of the weights, which gives you different functions. So if you sample, if you have the density of the weights, you sample a function, you plot it, it looks like one of those black lines, okay? And if you plot many of them, you get that, and the spread of those lines gives you the error bars, okay? The error bars are essentially a way of expressing how much variation is there in my lack of knowledge, in my uncertainty about the coefficients of the function. And this, which I'll probably also run over quickly, is doing this like point by point. I'll skip this. You'll understand it easily if you look at it. And then there's Gaussian processes, which I will skip. So Gaussian processes, I think it's still a very important thing to know today because there's a lot of material here that's used to understand the deep learning. Essentially, the idea of formalizing the function that I'm trying to estimate as a Gaussian process, okay? That with some covariance and some mean function. I'm going to skip this because it would take like 10 minutes to go over this. So I'll skip Gaussian process. It's very nice. It's extremely flexible. It's extremely powerful, extremely elegant. And it allows you to do the same things that we did as fully Bayesian regression. You can estimate uncertainty bands. You can control the spatial or vertical precision with which you do the inference. And in the linear regression case, you can do everything in closed form. As usual, linear combined with Gaussian, that's the best of all worlds possible in terms of estimation. You get everything in closed form. Everything boils down to just inverting matrices. So, but I will not, it has a lot of notation, so I'll skip it. I'll leave it in the slides. You can look at it later. And finally, because this is also important for modern stuff, especially for pruning, an alternative to ridge regression, which you can use, is instead of the squared Euclidean norm, so W2 squared, you can use W1. W1 is called the L1 norm or the one norm, which it goes by, popularly today, it goes by the name of LASSO, which stands for least absolute shrinkage and selection operator, although it had been used much earlier than when LASSO was invented. It has been used even in neural networks like more than 20 years ago. It can be seen as a map estimate as the other was, but under a different prior, but this is not important. What's important is that it yields sparse solutions. So suppose you're solving one of these regularized least squares problems where you add a norm, and I'm not specifying which norm is here because it's true for any norm that you put in there, minimizing the residual square of the residuals plus the regularizer, it's equivalent to solving the minimization of the residual subject to an upper bound on the norm. Okay, they're equivalent problems. If you know enough convex analysis or convex optimization, this is a basic result in convex optimization. If everything is convex, these two problems are equivalent in the sense that for any lambda that you want and you solve this problem, there is a choice of delta such that the solution on the right is the same as the solution on the left. Okay, so they are the same problem essentially. And so now when you instantiate these norms as being the two norms, the Euclidean norm or the one norm, so the balls of the Euclidean norm look like these. They are spheres or circles for p equals 2. The balls of the one norm are these squares on the left for p equal 1. P infinity is a square, but aligned with the axis. It doesn't really matter for now. And so when you solve these, essentially, this is the picture you have. Maybe you've seen this picture before. I'm sure you have, many of you. And this is kind of just a hand-waving justification for why when you, so those circles are supposed to represent level curves of the residual. They typically will not be circles, they would be elliptical depending on x, but they are smooth, they are ellipses. Okay. And so if you're looking for the intersection, for the point of touch between level curves which are smooth and the ball and the circle, the likelihood that they will meet somewhere in space, there's no special preference for being on the axis. Okay, but on the right side, if the ball that you're using to constrain the solution is the L1 ball, it has these spikes along the axis, and so it's very likely that the first level curve of the smooth part that touches the ball is exactly on one of those vertices. And when that happens, the other, in the two-dimensional case, the other coefficient is 0. Okay, so it's kind of hand-wavy justification for why the L1 norm yields sparse solutions. I'll skip this slide. And this is, remember the plot on the right was the ridge regression plot for the prostate cancer data with the degrees of freedom on the right. So what happens when you do ridge regression is as you increase lambda, the norm of the solution goes down. In the lasso case, as you increase lambda, well, the norm of the solution goes down, but also some of the coefficients actually go to 0. Okay, so depending on for example, if you are here, these coefficients, these, and these are not 0, but these 4 are all 0 because they reached 0 and they stayed at 0. Okay, so it gives you 0 solution, and 0 solutions are very important in machine learning because for many different reasons. But in linear regression, they mean that these coefficients are not very relevant to predict the response because they have 0 weight. In neural networks, it's very important because it's good to have many zeros because the model is cheaper. But that's another story. So how do you solve for ridge regression? You know how to solve this. It's just linear regression. It's just a linear equation. For lasso, this is much more challenging, and we will not look at how to solve it. It's another story. Okay. So this is the end of the regression part. I'm going to jump to classification, and a lot of things will be parallel. I'll go maybe 5-10 minutes in classification, then we stop. I'll go because we're kind of 15 minutes late. But yeah, I think I'll go faster in the classification part probably. Okay, same slide. What is classification? In a nutshell, produce a machine that predicts, estimates guesses, but now it's not a quantity, it's a class, 1 to k, from variables or features, x1 to xp. Maybe it's the core machine learning problem. The first problem that comes to mind if you think of machine learning is classification, at least to me. And the same problem, given a collection of training samples, find the best possible solution. Okay, I'll probably start this with probably it's not the usual way you see it, which is from a generative perspective, okay? It's interesting from my perspective because it shows the underlying assumptions that people do not typically make explicit when they're solving these types of problems. So the formulation is like this, very simple. You have Y is a class label, so it belongs to 1 to k. You have k classes. And you have prior probabilities. So class 1 has probability F1, class 2 has probability F2. Suppose you know those probabilities for the classes. And now you're going to assume that for each class, this is a bit technical, sorry, but it won't, again, if you don't understand this part, we'll reach a part where you can understand from then on without these. Suppose that in each class, you know that the observations follow some exponential family. What's an exponential family? It's a density that can be written in this nice form, which is the observations are in here inside an exponential function. Okay, we compute some function of the observations x, so as before, it's some feature map, and all you have to do is compute the inner product between this feature map and the parameter vector, which I'm calling eta. Okay, and then you compute the exponential of these. There's another function here which is not dependent on the parameters, and there's another function which also the one that guarantees that this is normalized. So if this was a Gaussian, this would be the famous 1 over square root of 2 pi, blah, blah, blah. In other models, it's something else. Okay, so it's just this. Suppose that you can do this. This includes many different, it includes Gaussians, exponentials, Bernoullis, binomials, Poisson, includes everything, okay, that can be written in the exponential family form. Now, basic machine learning, let's look for the maxima posteriori rule. How do you do this? Bayes rule, multiply the priors by the likelihoods, by the observation models, that's it, and find the maximum. Okay, since you're finding the map, I'm assuming you know what a map classifier is. If you don't worry, because this is not very critical for what comes next. 2 slides ahead. So you multiply the probabilities, the prior probabilities by the likelihoods. Because you're looking for the maximum with respect of y, you don't need the denominator of Bayes rule because it's just a constant. And you now take logs, drop constants, and you end up with something that looks very nice, which is you want to find the maximizer of these. So there's this guy here who's trying to force you to choose the most probable a priori class. So it's trying to choose this high. There's this guy here who's trying to force you to choose the class that has the highest inner product with the features of that particular observation. And there's another term here which depends on the normalization constant of the observation model. Okay, which essentially is trying to force you to find the class that is the more compact in terms of if this was variance, it was trying to force you to choose the model with the class with the smallest variance. The important observation is that it's linear in the features phi of x. Okay, and this is true, and this is true for if you have Gaussian observations, exponential observations, binomial observations, multinomial observations, categorical observations, Poisson observations. They all can be written like this. So you have a common language for all these models. Now, let's try to write the posterior probabilities. Okay, so how do you write posterior probabilities? Bayes' law, it's just P of y times P of x given y, and then you would divide by f of x. But let's not do that. Let's keep it as proportional to. Now, let's plug in the form of the exponential family. Okay, take logs. Let's define this psi of y as that quantity. Doesn't really matter. Okay, you get these. So now you know that f is proportional to the exponential of some inner product of parameters times features plus a constant for each class. So it's indexed by the class label. Okay, and now you want probabilities. So this is not normalized, it's just exponential of something. How do you normalize? Divide by the sum, right? Now, when you divide by the sum, you find out that the probability of each class given x is just exponential of this stuff divided by the sum of the exponentials of this stuff for all the classes, okay? And this is a familiar thing for everybody that's seen machine learning at least once, because this is called softmax, okay? Exponential of something times divided by the sum of the exponential of those things. The softmax, logistic, all of these. So the reason I like to do this, maybe because I'm old, the reason is because this shows explicitly the underlying assumption in terms of statistical assumptions on the opposite of the data that underlies using softmax and underlies the features that you use. Okay, so in practice, of course, the only way you have to compute these is if you know these eta, these parameters. Of course, you don't know, because otherwise it would not be learning. You don't know. You have data. One way of doing this, which is the simplest way, okay, you have data. Data has labels, and so the labels allow you to divide the x's into what are the x's from class 1, what are the x's from class 2, and so on. And from each of those, so for each class, you can estimate whatever way you want the parameters of the class from the training samples from that class, which you can, because you have the data is labeled, you can split it into classes and do that. And then you just take those estimates and plug them, and you get so-called GLM. GLM will stand for generalized linear model, or softmax, or logistic, or whatever you want to call it. Okay. This is not you say, but that's not how we do it, right? No one does it like this. Okay, so how do we do it? So how we do it is you start with the generalized linear model. Okay, we know that we have the probability of class Y given observation X given by the softmax transformation. Remember that I will assume that these guys are given, these are fixed. I'm not going to learn these functions. I'm only going to learn these parameters. Okay, these etas. Okay, and the size, and these ones I'm going to learn too. Okay, actually, I'm going to get rid of them soon. Okay, so what are the assumptions that underlie doing this? It's I have the data set, and the assumption is that each sample in the data set, each yi, is a sample from the corresponding probability distribution of the labels given the corresponding xi, which I know how to write because it's written up there. Okay, so each yi is sampled from these with xi in there. Okay, so it's very easy to write down. Okay, and now if I write compactly this eta to have all the parameters of all the classes and the zeta, all the zeta, but not you, all the zetas from the classes, we can write as before the log of the joint distribution of all the labels given all the axes and the parameters, which it's just like that. Log of a product is the sum of the logs, and then actually, if you can write it in a more explicit way, by instead of putting yi in there, okay, you put just a generic y, you sum across all the class labels, but you only keep the correct one. So if you're summing across all the probabilities, but you select there's this quantity 1 of y equals yi, which is 1 if y equals yi and 0 if it's not. It's called the one-hot encoding or an indicator function, which is a familiar form if you've used machine learning tools recently. It's the cross entropy loss. Okay, which is now what I'm going to do is I'm going to try to max. Actually, it's not the cross entropy loss. It's minus the cross entropy loss, because I want to maximize this, not minimize. So when I try to maximize this, what I'm trying to do is find the parameters eta and zeta that make the observed y the most probable possible. Okay, I'm choosing the model that makes the observations as probable as possible. That's the criterion here. And then we'll look at the binary case and then we'll stop. So in the binary case, which is the easiest one to analyze, you'll be very familiar. So the denominator is a sum over only two classes, 0 and 1. Let's call it 0 and 1. And you can divide both numerator and denominator by that quantity there, by an exponential of one of the parameters. And if you define the difference between the two parameters of the two classes and the two zetas, again, like that, you end up with something very familiar, which is exponential and I'm doing again the usual stuff to get rid of the zetas, which is assuming that one of the features is just 1. We end up with this very familiar function, which is exponential of something divided by 1 plus the exponential, which is the sigmoid, which you've seen, I'm sure you've seen many, many times, which looks like this. So the sigmoid is just a particular case of logistic regression for two classes. In this case, linear logistic regression, because the argument of the exponential is linear in the parameters, WT. That's not important. In 2 dimensions, it's easy to plot. It looks like this. These are level curves. And yeah, this is just how to compute the threshold. It's not important at this point. Okay, so I suggest we stop now. Okay. For how long? Half an hour? Yeah. Okay, half an hour. Where is the coffee break? Right outside. I'll be around if you have questions or comments. Glad to take them. Okay. Shall we continue? Okay. I hope you enjoyed pastéis de nata. If you don't know what it is, you'll find out. It's a little custard pies. I'm sure everybody knows what pastel de nata is by now. So yeah, let's continue. So my plan is to take about half an hour to conclude the classification part, and then leave the final hour for the optimization part. Okay, so we were looking at this special case of binary logistic regression. We have two classes. So we know how to write the probability of class 1, probability of class 0, which is 1 minus the probability of class 1. And so one classical way of writing these compactly is to use this exponentiation to y. Y is a binary variable. So when you raise something to 1, you get that thing. When you raise it to 0, you get 1. So that automatically selects which of the two factors appears, depending on y. And we've seen this before, so we can just take logs and simplify the functions and so on. And we end up with and multiplying by -1 to get it something that you need to minimize rather than maximize. And so the so-called negative log likelihood, NLL, given some collection of endpoints, is written like that. It's a sum across all the points of those that quantity there. Okay, so you have this linear part. Remember that xi is sample x, yi is the corresponding label, which in this case is either 0 or 1. So I'm using binary variables. That's the linear part. And the other part on the left that comes from the log it comes from the log of the denominator, from the normalization constants, which is the same for both classes. So that's it. We need to solve this. We need to solve this minimization problem if you're solving a binary logistic regression problem. Of course, unlike in the regression case, there is no closed form solution because unfortunately W appears inside a complicated function, which is the log of 1 plus exponential of something with W in there. So there's no way. You can compute the gradient. It's easy. But you cannot, if you equate the gradient to 0, you don't have a closed form solution. And so if you want to solve this minimization problem, you need to use an optimization algorithm. Okay, typically gradient descent, or actually before deep learning, there were tons, I mean, probably of the order of hundreds of papers on how to solve this problem, specifically this problem efficiently. And gradient descent is not even close to being very good for this. There are much, much better algorithms to do for this specific problem, for logistic regression in the linear case. Fortunately, so the objective function that you need to minimize is smooth and convex, so it should not be too hard to optimize. Okay, so it is not too hard to optimize. Let's look at, however, there's a little problem sometimes appearing here that people, I think, should be aware of, which is this is not a well-defined problem, okay, or it may not be a well-defined problem, okay? And the reason is this, let's consider this very, very simple case where you have only 2 points in one dimension. So you're in one dimension. So x lives here. You have point -1, 1, only one dimension. And the labels are, this point has label 0 and this point has label 1 as classes. It's because I don't want to confuse with the ones and the zeros. So notice that this 0, this 1 here, is not the same thing as this 1 here. They both look like 1s, but 1 is a number. The one on the left is a number, is the position of x. And the other one is the label of class 1. So to make sure that you keep that you engrave in your memory that this is a label, I will change this to A and this to B or something. Okay, they don't need to be numbers; it's just class labels. Okay, so that the fact that 1 1 may confuse it. And okay, so this is actually let's do it the other way around. Let's say that this is A and this is B. So we have a point, we are on the real line. We have a point in -1, a point in 1, and this one has label A, and this one has label B. So 2 classes A and B, okay? Let's say that the feature vector is just X itself. There's no mapping. W0 is 0. Just so we only need to estimate one parameter, W. That's it. It's just a number. And if you write down the thing we had before, for this very simple case of only 2 points in with those 2 labels, you can write it down. It's a sum of 2 terms, 1 to 2, because there's only 2 points. You write down the 2 expressions. We know what the points are. One is in -1, what the other is at 1. So we can do some little manipulation and end up with that expression there. It doesn't really matter what it looks like. What it matters is that if you compute the derivative, it's easy. Take the derivative of that. You know how to do derivatives. You conclude that the derivative looks like that. It's -2 divided by 1 plus exponential. Because 1 plus exponential is always larger or equal than 0, that's a negative number. Okay? Which means that this function has a strictly negative derivative. Okay? Which means that if you try to minimize it, where do you end up? You end up at plus infinity, because you're always going down, 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 as far to the right as possible. Okay? So in this case, the maximum likelihood or the logistic parameter estimate is undefined, because the logistic loss is not, it is as a negative derivative all the way to infinity. So you keep on going down. What's happening? Okay, it's very easy to see what's happening. It's like, so you are in one-dimensional case. If you have perfectly separable data, the best solution is to make the ones that have class 1 to have the probability of class 1 as high as possible, and you can do it by increasing W more and more and more. And the ones that have class label 0 to have probability of class 0 as high as possible, which is probability of class 1 as low as possible. And so what happens, so the W, our W is the kind of, the higher W, it's written on the right side, I don't know if you can see it. So the blue is W equals 1, 2, 5, and 20. The sigmoidal function becomes sharper and sharper and sharper and sharper, and it wants to get as sharp as possible, because that's what maximizes the likelihood or what minimizes the loss. Okay, so in this, if you have separable data, you cannot do logistic regression directly, because the problem is undefined. It will never stop. It will keep on increasing and increasing. So that's why people usually use some regularizer. Say you add the 2 norm to prevent that from happening, or the 1 norm. Both can be used. They're both well defined. Now, even for separable data, because they will prevent this growth, this infinite growth of the loss of the objective as you go to infinity, even for separable data, they're okay. So how does this look like in we already seen it at the beginning. For multi-class case, and we have more than 2 classes, okay? So we will compactly write, so that's we've seen this before, now without the W zeros and all of this, so this is the simplest version. So this is a softmax transformation, so this would be the, say, the scores. If you're looking from a perspective of a neural network, this would be called the scores. Okay. So this is just a softmax transformation of a bunch of scores, 1 per class. So you have X transpose W1 is the score of class 1, and X transpose WK is the score of class K. You just take these scores. These scores are just, you have a point, you compute the inner product with all the W's. Those gives you the scores. And if you just want to choose the most probable class, you don't even need to do this. You just find the highest score and that's done. Okay. But if you want to compute probabilities, you need to compute the exponentials that convert the scores. The scores are just real numbers. If you take exponentials, they will become non-negative. And if you do not divide by the sum, it becomes normalized. They become interpretable as probabilities. And if we write compactly the collection of all these W's as just W, this at the end just said this multinomial, we can write. We already wrote this before. The very famous cross entropy loss or log loss or logistic loss. It goes by all these names. You just sum across all the points, and then for each point you sum across all the classes. But you use the indicator function. So the indicator function is 0 if you're not at the correct class. It's 1 if you are at the correct class. So it keeps only that. It keeps only the log probability of the correct class for that point. Okay. And now we try to maximize these, which means you're trying to make the probability of the correct class as high as possible for each point, for all the points. That's what you're doing. So this indicator function sometimes it's written, it's the same as a one-hot encoding of the classes. So we'll use this notation. Y, bold Y, will be a k-dimensional vector that has a 1 in position that corresponds to the class of that point. Okay, I think you know about it. So it's just another way of writing. It's the same thing. Here, this would be the same as indicator of Y I equals K. Exactly the same. Okay, and then again, taking the fact that we know the expression it was in the previous slide. When you compute the log, remember, notice that the expression is exponential of something divided by sum of exponentials. When you compute the log of the numerator is the log of an exponential. Cancels out, you just get the exponent, which is the linear part on the right. But the log of the denominator, because the denominator is a sum of logs, and the sum of exponentials, I'm sorry. And the log of a sum of exponentials there's nothing you can do about it. It's just a log of a sum of exponentials. There's no simplification. And so that's why you have the term on the left. And you have, again, of course, the sum across all the points. So that's called that's the way of the log entropy. It's the cross entropy loss written for a logistic log likelihood. And so if you observe what's happening, when you try to minimize these, essentially you're trying to, because there's a minus sign here, okay? For the correct class, when this is 1, you're trying to push up the inner product between the parameter of that class and that particular observation. You're trying to make this inner product, trying to align W with the X for this class at each point. So you have to do this for all the points simultaneously, so that there's a trade-off between all the points in the training set. Okay. Now I'm going to say that this exists, but I'm not going to go into detail. Remember, we did it for regression. Suppose that we want more. We want to treat W not as an estimate that you find by just minimizing this loss and then you plug it into the model. That's what you would typically is done. But you want to take into account the amount of uncertainty, of randomness in the estimate of W. You can do that exactly as we did for regression. In regression, everything was very easy because it's just linear, Gaussian, linear, everything works out beautifully. But here it's much, much more complicated. The idea is the same. You have this Bayesian approach where you can write down the posterior for the parameters. And you can, if you want a predictive probability, you want the probability of the classes, okay, for a new point. But now integrating, I mentioned this a while ago, integrating over the unknown W. So I'm assuming that W is unknown, and I want to consider all possible Ws according to their distribution. I would need to solve this integration, but this is not feasible. Okay, you cannot do it. Okay, this now is you cannot even compute this. Okay, you cannot compute these expressions in closed form. You cannot do this integration. So the only case where, well, I'm not sure the only case, but one case where for sure Bayesian prediction is fully possible in closed form is linear regression with Gaussian noise and Gaussian prior. Everything Gaussian, everything linear. As soon as you move away from that, nothing works. Okay, it requires numerical operations. Okay, which is not problematic. And a lot of people do it, and it's very important. There's a lot of work on, even in deep learning, there's a lot of work on Bayesian deep learning where you use these to estimate uncertainty. Essentially, it all boils down to being able to compute the probability of the parameters given the observations, and then this is a model that you know, and then being able to compute this integral, which is often you cannot do it. But let me illustrate it. Okay, this is of course again from Kevin Murphy's book. Suppose you have that beautifully separable data, which is we know it's problematic, and on the right side, so this data, the blues and the reds, so no two classes. And those and the straight lines that you see there, I'll explain in a second what they are. They are separating hyperplanes, so they correspond to these positions where the logistic goes through zero. It's here. Okay, it's lines like it's a line like this, separation between the two class labels. Okay, for different choices of W and W. So this is just in 2 dimensions. So a straight line has 2 parameters. Okay, actually three parameters. In this case, it goes through zero. I'm assuming that everything is centered. So notice the origin is here. This is 0, 0. So I just need essentially 2 numbers. So on the right, what we have is the log likelihood, okay, which is unbounded, as we saw, because the data is separable. So the loss goes goes as a negative derivative. So the loss always goes down. It means the probability always goes up. Okay, and so that's shown on the right side by the fact that you have this open. So the log likelihood is going to infinity in this direction. Okay, actually, if you read the caption, that's what's written in there. Okay, actually it's written here. You see the maximum likelihood estimate is reached at infinity, and those points there on the plot 1, 2, 3, 4 correspond to those 4 lines on the left plot. So for example, the green, this point here corresponds to the 2 parameters that give rise to the green line here. Okay, so you have several of them. Okay, so this is on the right. Now, one very common thing to do to be able to handle this is to find a Gaussian distribution, so elliptical level curves that best approximate these. It's called Laplace approximation, and that's what you have on the right. So the right, you replace the log likelihood with a Laplace approximation of the posterior. Okay, we have a flat prior, and what is the Gaussian that best approximates these function? Okay, it looks like that. Let's believe so. I didn't do it. It was Kevin who did it. Okay, and then you can sample from this. Now this is a posterior. Now you can sample from this posterior. Okay, and if you sample from this posterior, you get lines like that. So this on the left, It's just the most likely W. It's the maximum of the posterior, only one point. So it's this red point here. If you take these parameters in this point, this is the line you get. It's the one on the center. This is just the different level curves. Okay, it's this one. But if you sample from this distribution, if you obtain different samples from this distribution, each sample corresponds to one line, one separating line. You get those samples there. You get those lines there. So these lines here are samples from this distribution. Okay, and for each one of them, you can now, if you average, if you compute what is the probability of each class according to each of these lines, and you average across all the lines, now you get nonlinear separation, which it looks like that on the left, which shows that, for example, here the boundary between the two classes is narrower. As you move away from the points, it's wider, and you get a measure of uncertainty for your classification, which you can, in this is all done numerically. So numerically and with an approximation. So as soon as you move away from linear regression, all this Bayesian stuff needs to be done with approximations. But I just wanted to know that it exists and it can be done. Let me talk now still about in classification, but with another view, a more agnostic view of what's going on when we're doing multi-class classification using logistic regression, which will allow us to generalize it in an interesting direction. Okay, think of it like this. So we have an input vector, the features that we have, and we have some thing that computes features, or scores, actually. Features and then scores. I don't care what's inside that box. Could be a deep network, okay? And in the end, at the output, I have scores, which I'll call Z1 to Zk, one for each class. Could be in the linear case, these scores, each of these scores would be, so Zi would just be the parameters of class I in a product with X, or with phi of X, if there's some transformation. And you have one of these per class. So it's just numbers, just a bunch of real numbers. And now I want to map, the idea is that the higher the score, the more probable it is that the class is that class. So if the second score is the highest, it's more probable that it's class number 2. So that's the semantics of the scores. Okay. So the scores are just vector. They're just real numbers without any constraints. Okay. But now I want to transform the scores into probabilities. Okay. And the probabilities have properties like they cannot be negative, otherwise they're not probabilities, and they need to sum to 1. Okay, so that's what's usually called a simplex. It's a collection of all vectors, such that the components are non-negative and they sum to 1. It's called a simplex. So I want something that goes from Rk into the simplex. Why is it called simplex k minus 1 and not simplex k? Because although it has k numbers, I only have k minus 1 degrees of freedom because I cannot specify the numbers as I want. If I specify k of minus 1 of them, the last one is already specified. It's 1 minus the sum of the others. So that's why it's usually called k minus 1. So if you think in mathematical terms, it's a k minus 1 dimensional manifold, but that's not. And now I want a mapping that satisfies these properties. If the scores are the same, I want the probability to be the same. Fair, right? If the two scores are the same, I want the probabilities for those two classes to be the same. But if one of the scores is higher than another score, then I want the probability to be at least larger or equal than the other score. It could be equal, but that it cannot be smaller. Okay? So I want a mapping that satisfies these properties. Let's see 3 possibilities. First possibility. Let's look for the vector of probabilities, the simplex, a vector that has non-negative quantities and sums to 1, that best aligns with Z, with the scores. So that has the highest inner product with the scores. What is the vector in the simplex? So the simplex looks like this in 3 dimensions. You've probably seen it. In 3 dimensions, it's just a triangle. It's a collection of all points that sum to 1 and are in the first order that are non-negative. So I have a point somewhere here, Z, and I want which of the vectors inside the simplex best aligns with Z. Finding what is it, okay? And it's well known that it's just the maximum. Suppose, why is this so? This is about, it can be shown mathematically, it's a linear program, but think of it. Suppose you have a budget of say 1,000 euros, and you want to invest in companies, and you know what is the return of each of these companies. These are the Z's. How would you distribute your money? If the only restriction is that you can only spend 1,000 euros, say 1k euro. Of course, you would spend all the money in the company that has the highest returns. That's the obvious thing. Suppose you know the return. I'm not taking into account uncertainty, risks, anything like that. You actually know that in this bank account gives you 1%, this gives you 1.2, this gives you 1.7, this gives you 0.3, and you have 1K euros to put in a bank. Which bank do you choose? You put all the money in the bank that has the highest rate, right? That's it. That's this problem that's being solved here. Okay, so the solution is called, this is argmax. It just says that you choose the score, the probabilities will be, if you have only one maximum, that's easy, it's all there. If you have two maxima which are the same, you have one half for each of those. You have a uniform distribution over the maxima, if there's, in case of draws. So the thing is that you have zeros unless you're not at the maximum. Second possibility is, okay, this is too risky. I want to hedge my risk. I want to distribute my probabilities a little better. And so you use entropy. So I'm assuming that you kind of know what entropy is. So instead of just maximizing this inner product, you add entropy. Entropy is a property of a probability distribution that is defined as is written down there. It's the probability, sum of the probabilities, log probability is the minus at the back. So h of p is there, which has these properties, which I'm sure many of you know. It's a non-negative quantity, so the entropy is always larger or equal than 0. And it's upper bounded, so the maximum value it can take is log of k, log of the number of probabilities. And the maximum is attained when all the probabilities are the same. Okay, so trying to maximize the probabilities, trying to encourage the distribution to be more uniform. Let's not have 1, 0, 0, 0, 0. Let's try to make it a bit smoother. Okay, and you can do that by, instead of just maximizing this, you add the entropy and you maximize the inner product plus the entropy. Okay, now if you solve these, okay, it's in the next slide, but I will not go through the proof. You end up showing that this is exactly softmax. You get the logistic transformation. Okay, so you have a vector of scores, and you solve this problem. What is the probability distribution that maximizes the inner product with the scores and plus the entropy? You get softmax, exponential of the z's divided by the sum of the exponential of the z's. This is why in a lot of literature, especially in speech, in machine learning in general, but in some subparts of machine learning, the softmax or logistic was also called maximum entropy mapping. Actually, you can do it. You can do it with some. You may ask, why do you just sum them? Why don't add some constants in one of the sides to balance how much you weight the inner product versus the entropy? You can, no problem. You can multiply one of them by a constant. Say multiply the entropy by 1 over beta, which is the same as multiplying the inner product by beta. It doesn't matter. And you can solve this. I'm not going to do it. This is the proof. You can see it in the slides. That if you do this, you get the result is softmax of beta times z. So you can take the scores, multiply all the scores by beta, do softmax, and that's what you get for the probabilities. So this is softmax as maximum entropy. Now, another possibility, which was actually proposed by André, who was here in the beginning, you saw him, and Ramon, who's also around, some years ago, 8 years ago, it's something called sparse max. And the idea was, it's very simple. It's kind of that idea that, why didn't I have this idea? It's so great. Okay, which is you have z here somewhere, a score, it's a vector. If you want a vector in the simplex that's as close as possible to z, the obvious thing is just project on z. Okay, find the projection of z on the simplex. Okay, which is written in mathematical terms as, let's find the probability distribution p in the simplex that as close as possible in Euclidean norm to z. And the solution is something called sparse max. I will show. I haven't explained what it is. Just define it. It's just the projection of z on the simplex. Finding the point on the simplex that is as close as possible to z. So that's called a Euclidean projection. So there's a projection here. You start at z and you end up at p. Okay, which is a probability distribution. Okay. Well, if you expand the sum of the squares above, you get p squared, right, plus z squared minus p in the product with z. Okay, if you expand the square. Okay, so the norm of z squared is irrelevant because it's just a constant, and so you can separate these into two terms. There's an inner product between p and z, and there's another term which is the norm of p squared. actually minus, because it's minus the square of the difference. Okay, and this actually ends up, it's not very important why, it's a form of entropy. It's a different definition of entropy called Thales entropy with a different formulation, which has different properties, but it's still a form of entropy in the sense that it tends to benefit, to favor more uniform distributions. And so in general, you can have exactly the same formulation that we had before, but where we replaced the Shannon entropy, the classical Shannon entropy, by any other entropy that you want. And by choosing different entropies, you obtain different properties. One of them is this thing called sparse max that looks like this. I'll show you in a second. So I'll show you an example of sparse max in a second. So all these functions, so argmax, which is given a vector of scores, finding the maximum. Softmax, which is given a vector of scores, exponentiating and then normalizing. Or sparse max, which is given a vector of scores, projecting on the simplex. They all satisfy these properties that I'll show. If you add a constant to all the scores, nothing changes. See, if you're looking for the maximum, if you add a constant to all the numbers, the maximum will still be in the same position. Okay? If you're computing exponentials and then normalizing, if you add a constant to all the arguments of the exponentials, it's like multiplying all the exponentials by the exponential of that quantity, and then it cancels out when you normalize again. And the projection, it's for the projection, if you're adding a constant to all the components of z, is like moving z away from the origin or towards the origin, but parallel to the simplex, because you're adding a number which is like 1, 1, 1, 1, 1 times constant. So you're moving parallel to the simplex. So the projection doesn't change. Okay, so all of them satisfy this property. Another thing is that they're permutation equivariant. If you permute disease and you apply the transformation, it's like permuting the result of the transformation. So if you change the first class with the second class, the result after the mapping will also correspond to changing the first class with the second class. And so this is how sparse max looks like in one dimension. So in one dimension, it should be the counterpart of the sigmoid function. So it's indeed like a sigmoid type of function, but it's not smooth. It looks like that. It's 0 up to a point, then it grows linearly, then it's 1 up to a point, which has, so for example, if the score is above 1 or below -1, the probability of class 1 is 1. It's not close to 1, it's exactly 1. Here in the middle, it changes, and in it's below -1, then the probability of class 1 is 0. Not small, exactly 0, okay? Which is different from the sigmoid, because the sigmoid is never 1 and never 0, only at infinity. Okay, so it has this regime where it is changes with the score, and there is regions where it doesn't change with the score. It saturates, which the softmax does not. And the thing happens again if you look at it in 3 dimensions. It's not very surprising. So an example: suppose you have 5 classes with those scores, whatever, some 5 numbers. If you do, of course, the one on the right is the easy one, argmax. Which of these numbers is the biggest one? It's the first one. So argmax just puts a 1 in the first position. That's it. Okay. Softmax corresponds to taking the exponentials of those numbers and dividing by the corresponding sum, and you get these probabilities. Of course, you get a higher probability for the first one because it has the highest score and so on, but they're all non-zeros. And sparse max is something in between. It's not just argmax, it's not all non-zeros, it's something in between. It gives you 2 probabilities, which are not 0. And of course, it depends on the numbers. Maybe it gives more than it gives. It could be dense even, or it can be sparse. It depends on where you are. And it's very easy to understand why. It's because the simplex, when you project, if you project from certain angles, the projection ends up at the boundary of the simplex. And in the boundary of the simplex, some components are 0. Okay, so there's also a parameter called temperature, okay, which corresponds to before, which you've probably heard it's much talked about in large language models. It's exactly what's going on here. If you, before you apply the sparse max or softmax or whatever transformation, you divide the scores by t, the effect of this is the following, and that's the reason, it will be the reason why it's called temperature. In the limit where this goes to 0, okay, both softmax and sparse max will converge to argmax. Okay. Well, I could explain it, but I won't do it. So it's like you like for a small temperature, only the highest probabilities will survive, and everything else will go to 0. And in the other end, If the temperature goes to infinity, okay, both sparse max and soft max will converge to a uniform distribution. It's like if you heat, all the energies are equiprobable. Okay, everything is shaking and everything is equiprobable. So this is the temperature parameter, which has exactly the same effect in sparse max and soft max. Actually, in soft max, it controls how peaked it is, and in sparse max, it also controls how sparse it is. Okay, so we can actually put all this together by noticing that what we are actually doing when we're solving classification problems is solving so-called regularized empirical risk minimization problems. So we have losses there. So now this formulation will, as we see in a second, will include linear regression, logistic regression, sparse mass regression. All these regressions can be written in that way. Maybe there's a regularizer, maybe it's ridge regression, maybe it's L1, maybe it's something like that. And you have a loss, which is an average of loss terms across all the data points. And for example, if you're doing logistic regression, this can be written by choosing L to be this thing, which you're already seeing. Actually, it's easy to show that this will give you the previous result. So F there is whatever function I'm using to compute the score. So those will be the scores. In this case, it's only binary. I'm back to the binary case, okay? I'm back at the binary case. Okay? Hinge loss, which will be for support vector machines. I will not go into that. So a loss that I really would like to minimize is the error loss, okay? Suppose that I could compute these. So I have training examples. I know Y, I know F. And because my classifier is of the form, so remember the classifier is something like Y hat, the sine of F of X, okay? I would like the sign of F of X to have the same sign as the labels. I want the label to have, I want the sign of F to be equal to the label. So in that case, I pay 0, I have 0 loss. If they're different, I have 1 loss, 1. And this is called the error loss, because this simply count, if I sum across the data set, I'm just counting how many errors that F is making. Okay, if I decide using the sign of the function. Okay. The problem is this loss is not continuous. It has a jump when F changes sign. So it's not continuous, so it's not convex either, because it's just a step function. And so we can look at everything we've done up to now for classification. Logistic, well, we only looked at logistic. We'll see in a second sparse max. But we could also use squared error loss. It's okay, we can use it as sort of convex and smooth approximations to the error loss. So the gray one here, which I'll paint black or blue or whatever. So this is the error loss, the one that's above, okay? It's discontinuous. So it's not convex. I cannot minimize these using gradient descent because there's no derivative at 0. And so no one does it. What you do, actually, it can be shown that it's NP-hard to solve problems in 0-1 loss. What people do and what we all do is replace the error loss by some convex continuous function rather than minimizing the number of errors. So the what's called binomial deviance there is the logistic loss. It's this orange one. It's the orange one you can see, okay? So we see that essentially what these losses are doing, they're trying to make the product of Y. So Y is either -1 or +1 in this case, trying to make the product of Y with F as large as possible, which means if Y is 1, I want F to be as high as possible. So for samples, training samples that have label 1, I want the score to be as high as possible for that sample. And for training samples that have label -1, I want the score to be as small as possible, as negative as possible. So I want them to be aligned. I want Y and the score to be aligned. That's what these loss functions are trying to do. So if we look at this quantity, 1/n, sum of the losses for all the training points, this quantity, we can see that it is essentially a sample-based or an empirical estimate of what we would really like to have, which is the expected value, okay? If I have infinite amount of data, which I don't, I never do, I would try to solve these. If I have an expression, if I knew the density of the data, which I don't, I could try to compute its expected value. This is what characterizes the performance of some function, of some classifier F. It's how well it does in expectation for that population. And I don't have access to these. So what we do is replace this expected value by samples, by an average over samples, which is what above. Okay, so this quantity, which is the empirical risk, Remp, is an estimate. It's an empirical version of this expectation. Okay, so that's important to know. Of course, this actual risk cannot be computed because F is unknown. So what we do is we have training data, so we replace the expectation by an average, by an empirical average. So that's what the empirical thing does. So what about sparse max? Can we put sparse max in this picture too? Yes, we can. And the path is quite simple, not as simple, but it's simple. So let's try to replicate what's done in the softmax case. So in the softmax case, as we saw, what we did is the classifier produces my probabilities for each of all the classes at my current classifier, and the loss is just minus the log of the probability of that class that's being predicted right now. Okay, this is what I want to do small, meaning I want the probability of the correct label to be as high as possible. Okay, and that's what I do there. And so ZC is the score of class C. Okay, and if we take the gradient, we find out that the gradient of this loss with respect to the parameters of the machine. So I'm assuming that these it's like kind of the scores are of the form phi of x transpose wy, so the usual scores. It's proportional to that thing which is softmax minus EI. Remember what EI is? EI is this binary vector that has 0, 0, 0, Z everywhere. It has a 1 in the position of the correct y. Okay, so that's the difference between softmax and EY. So if the machine was perfect at this moment, it would give a score of 1 to the correct class and score of 0 to all the others, and that difference would be 0. And you'd have 0, gradient is 0. I'm classifying perfectly all the points, stop. Okay? If not, what I have is for softmaxes of the wrong classes, I'm not doing anything. I'm not subtracting anything because there's zeros in EI. So I'm taking the softmax of the wrong classes, and the gradient is proportional to that, which means since I'm going to do gradient descent, I'm going to go in the opposite direction. I'm trying to decrease the probabilities of the softmax of the wrong labels. For the correct label, keep in mind that softmax is always less than 1. For the correct label, softmax, I'm subtracting 1 from it. Okay, so I get always a negative number. So since I go in the negative direction of the gradient, I go in the positive direction. So that's a negative number multiplied by minus 1. It becomes positive. Means I'm trying to increase the probability of the correct label. So by minimizing these, what you're doing is trying to follow a gradient that will increase the probability of the correct label and decrease the probability of the wrong labels. That's what comes out of reading what the gradient looks like. This is unfortunately, not directly applicable to sparse max. Why? Because sparse max will give you zeros here. You'll have some zeros, and you cannot compute logs of zeros. Okay? Softmax gives all non-zeros, so you can compute logs. Sparse max does not, so you cannot compute log zeros. So the idea that Andre and Ramon had, which is very smart, was, okay, let's go one step further and let's reverse engineer what I would like the gradient to be. I would still like the gradient to be of this form. Difference between sparse max and E and the indicator vector, so that the gradient has the same meaning. It's trying to do the same thing. Okay, and they found out that you can do that if you write the loss in this way. I'm not going to explain why, but it's just saying it's possible. Okay, you can write a loss such that the gradient looks exactly like it looked for the softmax, which is softmax or sparse max minus the indicator, which does the same. It's trying to increase the probability of the correct class, decreasing the probability of the wrong classes. And now if you plot it, it's the green line there. It has a very interesting shape because it's flat. Now it's actually, this plot is reversed with respect to the other. It really doesn't matter. It's like whatever. Think of this as the other one's flipped. It just depends on what you define by label. The important thing is that it is flat up to a point, then it's quadratic, and then it's a straight line up. So it's like it has properties of hinge loss, it has properties of squared error loss because it's quadratic at the origin at a certain position, and it has again then properties of hinge loss. So it's a sort of a classification Uber loss, but it's possible. The method is it's possible to do it for sparse max. Okay, I'm only 7 minutes late. Okay, let's jump. I should probably take questions in the middle, but okay, you can ask questions whenever you want, of course. This we just saw that you can solve. Let's now talk a little bit about optimization. Optimization is a fundamental tool for machine learning. It's all about optimization in the end. Okay. Once you do the models, most of the time you spend is solving optimization problems. That's why GPUs are so expensive, and why NVIDIA is the most highly valued company in the world, is because people are trying to solve these huge optimization problems. So we already saw this. Okay, we just saw this like 5 minutes ago, that all of these problems can be written in this way. It's the average of some loss across the data points plus some regularizer. And now we see that we've seen some of those. Quadratic loss for linear regression, just the sum of, it's just square of the difference. Logistic loss we saw. Hinge loss, it's for support vector machines we haven't seen, but we'll actually touch upon it later on. And the absolute error loss, which we will not touch upon today, but it would also make sense. There are many losses that make sense. There are many others. Okay. Let's very brief introduction to optimization. I'm assuming that you've seen some optimization. I just want to lay some notation on the table. If you have never looked at optimization, you're not going to learn it in 20 minutes, but you get, I guess, the gist of the key ideas and put in a certain way. Okay, so from the previous slide, calling theta. Think of theta have all the parameters of the model that you need to estimate. Okay, so it could be the weights, but in particular they will be the weights. So I want to find a minimizer of some function. So this function f is this thing that is all of these. So this will be my function f of theta. I want to minimize it. Okay, with respect to these parameters theta. Okay, so there are different types of minimizers, which is important to keep in mind. So there are global minimizers, which are points such that the value of the function is smaller than anywhere, no larger than anywhere else. Okay, and there are local minimizers, which are points that are lower. The function is lower than in the neighborhood, but not lower in general. Okay, so if you look on the right, so you have local minimizers, which are those points that are indicated, and a global minimizer, which is the one that is smaller than all the others. Okay, so that's important. So you can have, in this case on the left, global minimizers, and there are problems that can have infinitely many of possibilities. Okay, so of course, a global minimizer is of course also a local minimizer. If it's smaller than anywhere else, it's also smaller than in the neighborhood. But local minimizers may not be global. So local minimization does not imply global minimization. Convexity. This is a fundamental property for functions in minimization, which is, forget about the expression. It's like this. I'm sure you've all seen this. You have a function. If it is true that when you draw a line from one point in the graph of the function to another point on the graph of the function, if this line stays above the function, it's a convex function. Okay? You've seen this before, right? Yeah? Yeah, good. So you all know this. And there are different types of convexity. Namely, for us, for now, we need to distinguish between strict convexity and non-strict convexity. So strict convexity is when the line stays strictly above the function. It doesn't touch the function except at the endpoints. Of course, at the endpoint, it starts there. Now is open. You cannot have lambda equal 1 or 0. If you're not at the ends of the interval, you're somewhere in the middle, then the function stays strictly below the straight line. Okay, so the one on the right is a convex function, but it's not a strictly convex function because the function actually is touching the straight line touches the function everywhere. The one in the middle is strictly convex. The one on the left, it's not even convex because the line crosses the graph of the function. What are the implications of this? So convexity implies that all local minima are global minima. So if a function is convex and you found a local minimum, you know automatically that it's a global minimum. Okay, there is no. The other very important implication of convexity is that convex functions are continuous. Okay, you cannot have a discontinuous convex function. In finite dimensions, in infinite dimensions, you can. That's not important. You just imagine the function has a jump. If it has a jump, it cannot be convex. You can always, there's no way you can find this line that always stays above the function. So if a function is differentiable, I'm sure you're all familiar with this little object called the Hessian. It's the d by d matrix that has all the second order derivatives of the function with respect to all the parameters. Okay, it's called the Hessian. It's the generalization to more than one dimension of the notion of second derivative. Okay. If the function is twice differentiable, it has an Hessian, and so we can characterize convexity by looking at the Hessian. If the Hessian is positive semi-definite, then the function is convex. If the Hessian is strictly positive definite, then the function is strictly convex. Remind you what positive semi-definite means. So I say that matrix A is PSD, positive semi-definite. If any vector V times A times V is always larger or equal than 0. So if you compute the quadratic form using this function for any V, this is PSD. And PD, so A is positive definite. If V transpose AV is strictly positive for any V which is not 0, because for V equals 0, this is 0. Okay, so this is what positive semi-definite means. I'm guessing you knew it, but just make sure. So one thing that people who have not had a formal course in optimization probably are not aware of so much as convexity is coercivity. So coercivity is a property of a function that defined like that. No matter in which direction you go towards infinity, if you compute f of the argument, as the argument goes to infinity in any direction, the function also goes to infinity. Okay? It's called a coercive function. Now let's call G the set of global minimizers of some function. Okay? So if a function is coercive, okay, a function that goes to infinity in all directions must have a minimum somewhere. That's all there is to it. It can be proved formally, but that's the thing. But it's not an equivalence. A function may not be coercive, may have non-zero set of minimizers, but not being coercive. Simple example is a sine function. Sine function does not go to infinity. It goes -1. It oscillates. It has lots of minima. It has many minima. Think of an upside down Gaussian. Remember, think of a Gaussian function. Turn it upside down. It has a minimum somewhere. But it doesn't go to infinity. It goes to some flat value. It goes to an asymptotic. So it's sufficient but not necessary condition for the existence of minimum. Now another property, another implication of convexity which I had not mentioned, which is connected to this, it's important, which is strict convexity, which means that if a function is strictly convex, it has at most one minimizer. It cannot have more than one minimizer, only one. Okay. Unfortunately, it's not always the case. It's very rarely the case these days. So coercive and strictly convex, it has only one minimizer. Coercive but not strictly convex, it may have many minimizers. Convex but not coercive, it has no minimizers. We already saw an example. Logistic loss for separable data looks like that one on the right. It's not coercive. In one direction of W, the function does not go to infinity, it actually goes to some constant. So it has no minimizers. So actually, that's what I write below. Non-coercivity example, logistic regression on separable data. Descent directions. Okay. Descent direction. Suppose you are at some point. Okay, theta 0 somewhere. Okay, you're here. You're here. Theta 0. You have a function around you. So these are level curves of the function. A descent direct. Well, this is not a good place to be. Sorry, because it's close to the minimum. Suppose you're here. Theta 0. A descent direction is a direction in which if you move in that direction, the function goes down. You're at a hill, you can go uphill, you can go downhill. There are several directions that take you down. Of course, there's the one that takes you furthest down, but there are the directions that are descent directions. So a descent direction is any direction such that if you take a step in that direction, so this vector is eta, and the step size this is alpha. Okay. So if you take a step size
alpha in the direction of eta, the function goes down. So f of that new point is less than the function where you were, okay? For some alpha, there's some step in that size, okay? If the function is differentiable, being a descent direction is the same as saying that the inner product of that direction with the gradient is negative. It means that you're going in the negative direction of the gradient, okay? If the function is differentiable. This is what the definition of a descent direction is. So if you have a differentiable function, if some point is a local minimizer, it implies that the gradient needs to be zero, okay? Because there's no way you can go down from there. There's no descent directions. If you're at the minimum, there's no way you can go down. You're at the bottom, okay? But the implication, the reverse implication is not true, okay? You can have gradient be zero, but this not being a minimizer. So the classical example is this saddle point. At this point here, this is not a minimizer, it's not a maximizer, it's called a saddle point, because in one direction it's a maximum, in the other direction is a minimum, but it's that point, at that specific point, the gradient is zero, okay? So the gradient is zero, but it's not a minimizer, okay? This would not happen if the function was convex. This function, of course, is not convex, as it's clear to see. So only if you have convexity, then local minimum.
Direction.
No, everywhere. The gradient is zero in any direction. The gradient is zero. The gradient is not. The gradient is a vector that you compute there. Sorry. It's not even a local minimum. It's not even a minimum. It's a minimum in one direction. It's a maximum in another direction. But since the function is not convex, that it doesn't mean anything. It just means that it's a saddle point. Okay. So if f now, that's what I was saying. If the function is indeed twice differentiable, then we can show that if a point is a global minimizer, then, and if and only if, the gradient is zero. I'm not going to show it as a proof in the slide if you want. It's it's one of those trivial proofs from second lecture of an optimization course. You just do the Taylor expansion, you use the fact that the Hessian is positive semi-definite because the function is convex, and you end up with the conclusion that's at the two bottom lines, which is the gradient is zero implies that the function is larger or equal than it's a minimizer, then the gradient needs to be zero. It's very easy. It's just boring to do it now. It's simple. So, but fundamental, the conclusion is that if a function is convex and twice differentiable, then you are at a global minimizer if and only if the gradient is zero. Okay, this can also be proved without Hessians, without differentiability, but it's much more complicated. You can read in the book if you want. Okay, so now that we know all of these characterization of functions, how does gradient descent work? Okay, it's a natural thing to do. If you're not in a minimizer, take a step in the direction of the gradient of the negative, the gradient. Okay, the gradient points in the direction of the highest increase of the function, and you go in the other direction. You go in the steepest direction that you can go in terms of decreasing the function. So how do gradient descent algorithms work? Very simple. It's just like that. You start somewhere, and for each iteration, you choose a step size, say alpha t. You theta, which is theta t, by subtracting from theta t minus 1, the step size times the gradient at where you are. Okay, this is called gradient descent. There are many ways to choose alpha. This is a huge, choosing alpha to make this work is a huge research topic. And it's a lot, even today in the sophisticated algorithms to do this, we'll touch upon them at the end in a second. Okay. And now, of course, you need some stopping criteria. Okay, there are many stopping criteria. One of them is something like, let's look at the norm of the gradient. When the norm of the gradient is sufficiently small, below some threshold, probably I'm very close to a minimum, so I'll stop there. Actually, interestingly, this can be analyzed and can be proved to converge, and we can have exact optimal choice for the step size. In the case that where we started all this lecture, which is linear regression. Suppose you want to solve least squares, and you don't want to do it in closed form because this is all too big. You want to do it So you take your squared error loss, so the residual sum of squares, whatever you want to call it, expand that, redefine those things to be called, so x transpose x will be called q, x transpose y will be called p, and the other term is irrelevant because it's just a constant. Okay, I don't care about it. Okay, let's try to solve these using gradient descent. What is the gradient of that? What is the gradient of a quadratic form? Is just the matrix times the vector. Gradient of an inner product is just the vector. Gradient of a constant is just 0. So the gradient of these is just this. Notice that this is the gradient as a nice interpretation, which is q theta is just x transpose x theta, and x transpose theta is just y hat, right, at some point. So this is theta hat if you want, okay? And p is just x, so minus x transpose y. So this is this x transpose. So if you end up with if you have 0 residual in the predictions, the gradient is 0. You stop there, okay? Otherwise, you need to take the residual and project them on the rows of x to get the direction of the gradient. So that's what the gradient looks like. The Hessian, or a quadratic function, is just the q, just a q matrix. Okay, it's like what is the second derivative of a function that looks like 1/2 of ax squared? It's just a. Okay, that's it. And so using these, we know that the Hessian now, this was left from 2 hours ago to prove that this is a convex problem. Now we know, because q, we know how the Hessian looks like. It's x transpose x. We can compute this thing theta transpose q theta, which is what we need to show it's positive to show that the Hessian is positive semi-definite. It's very easy because q is just x theta. So sorry, q theta is just can be written like that. It's just square norm of something, which is always necessarily larger or equal than 0 because squared norms cannot be negative. Definite. So we know that f is convex. So gradient descent has the chance of working. Okay. Actually, more. If x is full column rank, if x transpose x is invertible, then q is actually strictly convex, and so we have a unique minimizer. Now let's take some step size. Let's choose a step size. So we now can write iterations. Remember that this is the gradient. This is the gradient of f computed at theta t. Okay. So just wherever you are minus step size gradient, the gradient looks like that. Okay. Let's do this little trick of subtracting from both sides one minimizer. Let's say that theta star is a minimizer. The minimizer is unique. If in the case where q is positive definite, the minimizer is unique. So at any point that satisfies gradient equals 0 is a minimizer. So let's put 1 there. Subtract from both sides. Okay. So we have it. And replaced p by q theta star. Now, if I now put this theta t minus theta star in evidence, this can be written in this way, nicer way. Identity minus alpha q, okay? Which shows that now if this is just for one iteration, if I do it for t iterations, starting at iteration 0, I see that notice that this is the error. This is the error then wherever I am right now, theta t and an optimal theta, which is theta star, shows that the error is evolving like that. It's I minus alpha q raised to t is the number of iterations, times the initial error, which is where I started, theta 0 minus theta star. Okay, so what shows that what controls the convergence is this matrix I minus alpha q, because I'm going to multiply this matrix by itself at each iteration. It keeps on being multiplied by itself. Okay, so we know that for a unique minimum to exist, I need q to be positive definite, okay, which means I need the minimum eigenvalue of q to be positive. Those of you remember your linear algebra. Okay, now I have a few facts which I'll kind of skip. Yeah, we'll go to the stochastic approach in a second. Okay, so what we can show is that and making a long story short, the following, okay? If you choose as step size this quantity, the inverse of the maximum eigenvalue of matrix Q, and remember that Q is X transpose X, is your data design matrix, okay? Then you have this quantity called condition number, which is the ratio between the maximum and the minimum eigenvalues, okay? And what controls the iteration is the following. So the norm of the error at iteration t times the initial error norm. And this goes to 0 because k minus 1 over k is a number that is less than 1, okay? And it depends on how much smaller than 1. If it's much smaller than 1, this converges very, very fast. If it's close to 1, this converges very, very slow, okay? So the best option, the best case is when all the eigenvalues are not too different from each other. In that case, you have a nicely conditioned matrix and the convergence is fast. If you have very large condition number, which means very small minimum eigenvalues and very large eigenvalues, then condition number is bad and it converges slowly. Actually, if you know the minimum eigenvalue, which often you don't, it's very easy to estimate the maximum eigenvalue. It's very hard to estimate the minimum, but in some cases you know it. There's actually an optimal value, which is even better, which I'm not going to explain why, which is the inverse of the average between the minimum and the maximum eigenvalue. And in this case, you can have a slightly better convergence because you can add this plus 1 here. It's no big deal. It doesn't change much. Okay? This type of what's happening is that the error at iteration t divided by the previous error is less or equal than some constant that's less than 1, which means the error is going down by a factor gamma. Okay? So it's called linear convergence because the error is being multiplied by a constant that's less than 1. Okay? So what controls the difficulty is the condition number, which is the ratio between the maximum and the minimum eigenvalue. And so, for example, on the right, there'd be a problem with a small k, good condition number, because there's the two directions are essentially have the same variance. In the other case, you have a very narrow objective function. So that in one direction, the eigenvalue is very small, in the other, it's very big. So it takes a long time to converge, okay? It has a huge impact, okay? That's example. On the bottom from Francis Bach's book, which I'll mention in the end. So on the left side, so the blue line, and in the blue line is a case, it's a problem where the eigenvalues go down as 1 over k in their index. So the first eigenvalue go down as 1 over k squared, which means the first eigenvalue is 1, the second eigenvalue is 1/4, the third eigenvalue is 1 over 9, the fourth eigenvalue is 1 over 16. They go down much, much faster, which means that the small eigenvalues are much, much smaller than the first one. And so if you look at what happens to an algorithm to solve this problem, as time goes on, iterations on the horizontal axis, you see that in the case where the eigenvalues go down but not super fast, the algorithm actually converges. After 4,000 iterations, the log of the residual is down to -6. So you have 6 decimal positions that are stable now. Whereas in the other case, if the eigenvalues go down really fast, the problem is very poorly conditioned, and the algorithm does not converge nearly as fast, and it takes a while. So all these matrices are conditioned, has a huge impact on the efficiency of these optimization algorithms. So actually, this can be generalized to the general convex case. I'll go here. It's quite simple to explain. The idea is that instead of looking at Hessians and eigenvalues of Hessians, there's a much simpler characterization, actually, which contains the other one, which is we can assume the fundamental property is something called L smoothness, which is to say that the gradient, the difference of the norm of the difference of the gradient between 2 points is upper bounded by the distance between these 2 points times a constant L. If this is true for any pair of points, theta and theta prime, for some L, we say that the function is L smooth. I'll show you a picture in a second. If f actually happens to be twice differentiable, then this corresponds to saying that Hessian is less or equal than L times identity. And there's another property which is mu strong convexity, which is to say that, well, I'll show it in pictures. Function f here, it's the black line. Oh, this is slow. Whoops, there you go. Function f. I said that the function is mu strongly convex. If the function is above this red line, this red, the function that's labeled as strong convexity, my function is always above a strictly convex function. There's a strictly convex function, quadratic and strictly convex, and my function stays above. That's strong convexity. And there's another function, which is the green one, which is convex, and my function stays below it. So what happens if I have an L smooth and mu strongly convex function, which is my f of theta, it means that there are two quadratic functions, such that my function is bigger than one and smaller than the other. Okay, I have a sandwich of quadratic functions, and my function stays between them always. Okay, and if this is the case, all the results before apply to this function f. Okay, I don't know why this is so slow. So mu strong convexity implies strict convexity, but it's not the same. It's not implied by. And mu strong convexity implies coercivity, right? Because I have a strictly convex function. So if it's strictly convex, it goes to infinity. If my function f stays above, it also needs to go to infinity. So it's being pushed up by the lower bound. Okay? And you can always achieve these by regularizing. If you have your function f that you want to minimize and it's not mu strongly convex, as soon as you add something like norm squared, like do weight decay in neural network parlance, it becomes mu strongly convex and much easier to optimize. Okay? And now I'm not going to prove anything. I'm just going to show what the results look like and what they mean, which is very important. So if you have, in the case of only having L smoothness, you can show that the function value goes down linearly like that. It's some constant less than 1 raised to t times the initial error. So it goes down. I'll show you a plot in a second. If mu is 0, so it's not strongly, that's for the strongly convex case. If mu is 0, it's not strongly convex. All you can show is that the gap, the optimality gap, goes down with 1 over t. And 1 over t is very, very, very different from some number less than 1 raised to t. Okay? 1 over t goes to 0 much, much slower than the one above. Okay? Let me show the plot. Here you go. So sublinear, it's not the one. So linear convergence is the one. So sublinear is 1 over t, it's the red line. So this is error in log axis. So the red line is something like 1 over t. It's what the best you can get without strong convexity. Okay, it's bad. The triangles, the gray triangles are which is what we really like to have, which is when you can show that it's up there. I don't know why it didn't. Yeah, it's up here, which is when the error, whatever you're minimizing, this is the residual, divided by the square of the previous residual goes to a constant. And this constant is like, notice that the square at the bottom is important because it means that your error is smaller than the square of the previous error times a constant. And if the square is small, if you square it, it becomes even smaller. So it goes very fast. It's accelerating. That's why it looks like this. But it can be shown that it's not possible to attain quadratic or superlinear convergence using only gradients. You need more information. You need, for example, to use the Hessian of the function, which in general you don't want to do. What is the implication of these for our for machine learning and for optimization? So why did I go through all this optimization? Because in some of these parts lies the reason why machine learning works in modern systems. So let's go back to the least squares regression problem. Okay, it's the simplest one to analyze. We're trying to do regression. We know the problem is convex. Now we have less data than parameters. Remember, we have in a small n, large p. So my matrix, X matrix, is wide and short. So there is no, the minimum eigenvalue is 0, because I cannot invert this matrix, I cannot solve. But let's ignore that. Let's pretend we don't know. And let's do gradient descent and see what happens. We know how to compute the gradient. We already did that. Let's do gradient descent. Okay. So now we know that Q is X transpose X, so we can rewrite the gradient descent like that. We can move X transpose outside because P is X transpose Y. We can write it like that. And they already mentioned this. What we have on the right is the residual. So this thing here, Y hat and Y, okay, at each iteration. Now let's do this trick. Let's multiply on the left by X, everything, and subtract Y, okay? I've buried me. I know it's not nice to be to listen to proofs, but this is one, it will give an interesting result. So when you multiply on the left by X, you get X times theta, it's just Y hat. You subtract Y, you do the same on the right, and you get that expression there. Okay? So now let's simplify. Again, it has a very similar form we had before, but now it's not in the difference that we're looking at now, it's not the thetas, but the Ys. The Ys are the predictions. Okay? Shows that the prediction error, so Y hat of t plus 1 minus the true Ys, is equal to that matrix there, I minus alpha x xt, times the previous residual, the previous error in predictions. Okay? So, but if x xt is large, if this matrix, not xtx, this one is singular, you cannot invert it, but x transpose, you can invert it. That's the one you compute when you do minimum norm solutions. Okay? If this one is invertible, it has a minimum eigenvalue which is strictly larger than 0, which is likely because you have many more parameters than points, and this matrix is n by n. Then for any choice, say for alpha, the one choice we did before, it could be 1 over lambda max, then the predictions go to 0 because this matrix is less or equal than identity. It's less or equal than 1, so it's the prediction errors are going to 0. So this is sort of surprising because what it shows is that you have a problem that does not have a unique solution because you have fewer points than parameters. You forget about it. You do gradient descent on the parameters. It cannot converge because there is no unique solution for the parameters, but the prediction errors are converging. Okay? You don't care where the parameters are going because what happened is that okay, so if you ignore the non-uniqueness of the solution and you still insist on doing gradient descent, you convert to a minimum training error loss. You go to 0 error loss. Somewhere in parameter space, it doesn't matter, but you guarantee that you minimize the error loss, the training loss. Okay, so this is sort of what explains why doing gradient descent in overparameterized models works. Okay, this is a very simple analysis in a linear case. It's very hard to transfer to translate these analyses into deep networks, but the idea, the essence of the idea is this here. Okay, so in practice, you can never do these gradient descents when n is really large or when p is really large. You always resort to gradient descent. So what is stochastic gradient descent? So what is stochastic gradient descent? Is the fact that you notice that for large n, computing exact gradient is expensive because you need to sum across all the data points. Which why is it so slow? What's happening? You start somewhere as before, and now for each iteration, you sample one of the points at random, you choose a step size, and now you take a step in the negative direction of the gradient, but of only of one specific component, of only one term, one of the elements in this sum. Not the sum, just one of the elements. Why does this work? I like this motivation around computing a mean. Suppose you want to compute a mean of a collection of vectors. Okay, very easy problem. I give you n vectors, you want to compute the mean. You just sum all the vectors, divide by n. It's easy to show that the mean of a collection of vectors is a solution of an optimization problem. Okay, think of a collection of points. Oh. Oh, damn. Collect. Okay, this is mu. It's the average of those points. That point is a solution to the problem of minimizing the squares of the sums of the distances between mu and all the points. Okay. In the one-dimensional case, it's on the right. It's on that plot there. Squares of distances between the point. That's the mean of all those blue points. It's the red point. It's what minimizes the sum of all those squares. Okay. Let's look at these from a stochastic gradient descent perspective. So instead of minimizing the whole sum, I'm going to start somewhere. I'm going to start at 0, actually. And then I'm going to do the following. I'm going to go through every point and do the gradient descent step. So as I'm whatever I was, theta t minus 1. I'm using step size 1 over t. So the step size is going down. And what I do is I take the gradient of, what is the gradient of 1/2 of the norm of the distance is just 2 times the distance. That's it. And so if you do that, you'll realize that you end up with t minus 1 over t. Computing a mean sequentially. If I tell you, I computed the average of these 70 points and I get this result, but now I have an extra point. How am I going to do? It's very easy. You take that average and multiply by 70 to get the sum from which you computed the average. You add the next point and divide by 71. So you don't need to redo it. So you can do it incrementally. So exactly this is what's happening here. If you do stochastic gradient descent on the sum of the squares of the differences using step size 1 over t, you recover this algorithm, which is very well known to compute means in a recursive way. Okay, which you have the mean, you unnormalize the mean to get the sum, you add the next point and you renormalize by dividing by n plus 1. Okay, so this is the motivation. I think it's a very nice motivation for stochastic gradient descent. The other motivation, which is actually more formal, is now suppose, which is very similar to the previous one, suppose you want to estimate the expected value. You just compute the expectation. Suppose you don't. Okay. So now it can be shown that the expectation of is exactly as before, but now for the whole population, that the expected value of a random variable is the number w, or vector. In this case, it's just a number. Suppose it's a scalar. It's the vector that minimizes the expected value of the square of the difference between the variable and that point. It's like the picture that I did in the previous slide with the red points and the mean. Instead of 10 red points, I have infinitely many red points. Okay, and then I want to find the expected value. Okay, so if you do stochastic gradient descent now by sampling x every time, so to update the sum, what you do is you take the previous sum, you take a new sample xt, and you do the gradient. The gradient is just a difference as before. And so it's easy to show that this will give you precisely the average of the samples. Okay, precisely. And now if you compute, I'm going to skip the details, but I'll just show you the result. Final result is that the so-called optimality gap, which is down here, which is the difference between the expected value and the optimal risk, which is the variance of the variable, it goes down in sigma 2 over 2. Sigma 2 over 2 over n. So it's going down as n. So you are actually converging to the same thing that you would get if you had infinitely many samples. Because it's going to 0, which is the optimal possible cost that you could get, which is sigma 2 over 2. So why is this relevant for machine learning in general? Because remember, what you would really like to compute is this. It's the risk. It's the expected value of the loss. This is what you would really like to compute. But this would require knowing the joint density of the labels and the inputs, which you don't, or having an infinite amount of data. Okay, you don't. So let's see what happens if you do gradient descent. Let's try to do gradient descent on that. So to do gradient descent on the risk, which you cannot, but the gradient and the expected value can permute, right? Because the expected value of the gradient and the gradient of the expected value is the same. They're both linear operations, so you can commute. So the expected value of the gradient is the same as the gradient of the expected value. This is the key observation, okay? Which means that if you take the gradient at any point, its expected value is actually the gradient of the risk, okay? And that's great, because then what you have to do simply is you do stochastic gradient descent, taking samples, you just sample from the data, you have observations, pairs, x, y, you sample, you compute the gradient, you go down in the direction of that negative gradient with step size alpha t. And so if you compute the expectation of that equation by computing expectation in both sides, simply because the expectation of the gradient is the gradient of the expectation, which is the gradient of the risk, you get that when you do stochastic, you're essentially doing gradient descent on the actual risk, okay? That's what's written there. In expectation, stochastic gradient descent by sampling from data is just gradient descent on the expected risk, which is great, because this is exactly what you really wanted to do. So this is a property that you get from stochastic gradient descent, which you could not get from batch gradient descent, because you can simply not do this. So this is now I had some slides on convergence stochastic gradient descent, which I'm gonna skip. I'll just show you the difference when well, I won't. I'll just show you a picture that kind of summarizes what I've been saying up to now in this last part of stochastic gradient descent. If you don't follow Gabriel Peire on Twitter, I highly recommend it. Write down the name. Anyone here knows Gabriel Peire? Good, a few. So follow his X account. Every day, for many years, he tweets informative and very pedagogical. This is a one, I don't know, from 3 or 4 years ago, where he explained how stochastic gradient descent works in the two cases that we saw. When you have a finite sum, so you want to minimize a function that's a finite sum of functions, or you want to minimize a function that's an expectation of some function. This is the finite, you draw uniformly from the functions, or you draw randomly from the density, underlying density. And in both cases, if you use step size 1/k, it's guaranteed that the error is going down as 1/k. This is a very old result by Robbins and Munro. That's why the call. So I urge you to follow Gabriel Peire on Twitter. I have 5 more minutes. I don't want to go more than 5 more minutes. So what happens in particular case of gradient descent in the linear classification case? So in the linear classification case, the loss can be written in that simpler form, which you already saw, because we saw these loss curves, lots of them. And now I'm saying that classified is linear, which means that this is my function. The function f of x and theta is just theta times x. I'm working with a linear classifier. Y is the label. The loss is, say, the log loss, or the hinge loss, or the sparse max loss. Choose. Doesn't matter. Okay? There they are. Some loss. Okay? Now, the important thing is that if we compute the gradient of these little losses, we find out the following. It's just composite function. The gradient of that is just the gradient of little l computed at the argument times the gradient of this inner part. But the gradient of the inner part, because it's a linear function in theta, it's just this. It's just x. It's just y times x. Okay? Which shows that every gradient of this function is some number times x, the corresponding xi. Okay? So the gradients are collinear with the samples. Okay? So you're always moving in the direction of the sample. So each stochastic gradient is looked at. Okay? It doesn't move in any other direction. It's in that direction. Okay? So for example, if you do this for the hinge loss, so the hinge loss is, we already saw it a while ago. It looks like this. It looks like this. The gradient is -1 if you're, this point is 1. It's actually some tau, actually. It's -1 if you're to the left of tau. It's 0 if you're to the right of tau. So you can compute that derivative. And if you do this, it's easy to show that stochastic gradient descent will do this update, which is if the linear part, the output of the linear function times the label is less than that tau threshold, then the gradient is simply yi times xi. And if it's in the same, if it's larger than tau, it's just 0. Okay. And when you do this, you obtain something called the perceptron algorithm. Okay. Very famous, 1957. It was the first sort of neural network learning algorithm, which later was rediscovered as being stochastic gradient descent on some version of the hinge loss, which we all like to show. This, I don't know if you can see it. There was a lot of hype about these. This is 1957, an article on the New York Times, where Frank Rosenblatt, designer of the perceptron, conducted a lab. He said that the machine would be the first device to think as a human brain, as do human beings. Perceptron will make mistakes at first, but will grow wiser as it gains experience, he said. And he said that soon perceptrons will be fired to the planets as mechanical space explorers. So they're extremely excited about this in 1957. It didn't happen like this. So there's a long story around it, which I'll have no time to go over. So actually in 62, which was 62 years ago precisely, there was a theory result proved about these, that it converges. The final thing I want to go over, which is again connected to this double descent and why overparameterized models work, is implicit regularization, which results directly from here. I'll just take 2 more minutes and then I'll stop. So remember the gradients for the linear case, for the linear classifiers, the gradients look like this. They are proportional to x, and there's a constant behind, which is the label times the gradient of the loss. It's just a number. It's just a scalar quantity. So it's always, the important thing is that every time you update the parameter, you are moving in the direction of one of the axes. Okay, and even if you do batch, if you do for the whole data set, it's the same. If you do mini batches, which is instead of using just one sample, use a small collection of samples, it's still the same, because it's always a linear combination of points. So you're always moving in a space that has linear combinations of points, which means that if you start at 0, your parameter estimates are always in the span of a collection of the axes. What is a span? The span is a collection of all vectors that can be written as linear combination of those vectors, because you're always adding constants times one of those vectors, always. So you're always in the span of those vectors. And so what happened is that if there are multiple theta stars that have 0 training error, which we saw there are, because we are in an undetermined case, so we have an overparameterized model. There are many choices of theta that lead to f being 0. If the predictions only depend on these inner products theta times xi, okay, this corresponds to I never move in a direction that is irrelevant, that is useless, because it will have some norm which is irrelevant, because it doesn't minimize, it doesn't contribute to diminishing the error. And in fact, if I do gradient descent, I'll never go there, because I'm always staying in the direction of the axis. Okay, so it means that without having to impose this, solving the minimum norm problem. I'm in an overparameterized regime. I know I can get to 0 training error. I do gradient descent, and by doing gradient descent, I'm implicitly solving this problem, which is different from the one I started with. I'm imposing that I stay at 0 training error, and that the norm of theta is minimized, which is the second half of this double descent side. So this shows that just by doing gradient descent and starting at 0 in linear models, you're automatically living in the modern area of the modern regime, where you have minimizing the norm under the constraint that the training loss should be 0. So this is the overparameterized or interpolating regime. And also if you want more, you can do explicit regularization, which I will skip, because it's in the interest of time. Let's see where we are. And so, unfortunately, because I slipped a little bit, there is a few things that I will skip. How to go from just standard stochastic gradient descent to mini batches. What's the effect of having mini batches? It decreases the variance of each step because you're averaging over a few samples, not just one sample. It has importance. Momentum is extremely important. It's not just moving. Let me just show this example. Suppose you are here, you're going down in this objective function. You are here, okay? If you just did gradient descent, you would move in this direction because this is where the function is going down, okay? But momentum says you should move in a combination of the gradient, negative gradient, and the previous step that you took. The previous step that you took is from here to here. This was the previous step. So if you add the two, you're going to go in that direction. So momentum, it's like thinking that the point that's going down the function has mass, and so it wants to continue going in the direction where it was going. And it makes a huge difference in optimization. The modern algorithms, or the roots of the modern algorithms that are used in deep learning, adaptive gradient, you can read it in the slides. Adaptive gradient called ADAGRAD, RMS prop, and the very famous ADAM, which was published in 2015 and already has 185,000 citations and 184,000 citations in 9 years. Okay, this is ADAM. And so in terms of conclusions, and I have a set of conclusions, which are very detailed, which boil down to, let's have lunch. Okay, thank you. I'll be around the whole week, so feel free to ask questions, or you can ask them now. I'm available now, of course. Everybody's hungry.
So just one thing about lunch. So follow Mariana. She will indicate the way. I think that's the plan. I don't know, Mariana. Do you want to add anything else? It's upstairs, straight ahead, so it's pretty close. And after lunch, we will get the labs at 2 p.m. Right?